Okay, we're live. I don't know if you learned. I think people have started to see that how much better the recording video quality is. Are we good yet, or recording? Okay, great. So hello everyone, welcome to the afternoon session. Our speaker today, and for the next 3 days I guess, is Anima Anand Kumar from UC Irvine. And she's really been leading the way in this new area of research on spectral methods and tensor decompositions for machine learning. And so we're going to find out lots about that today.
Thanks a lot, Zico, and also Alex, who's not here, for the invitation. I see it's a great set of lectures here, and I'm excited to be part of this. So in this series of talks, I'll be talking about how to learn latent variable models. So by latent variables, I think most of you know they mean like something is hidden, like you don't have observations from this set of variables, and still how can we learn them with guarantees? So that's what I mean by like guaranteed learning. And then the question is, where do these tensor and spectral methods come in? So let's start with a set of applications where latent variables are relevant. Perhaps the most basic machine learning task is clustering. Right, so in its very basic form, we have a set of data points, and I'd like to classify these data points into different groups. So that's what I mean by clustering. But we'd like to, in many tasks, think of model-based clustering, where we actually have a probabilistic model for the data points. For instance, you can think of each group as representing a different distribution. For instance, it could be in the simplest setting, just a Gaussian distribution for each group, and then you have the sample drawn from one of these given distributions, right? So the simplest case would be a Gaussian mixture. So this task of classifying these data points into different groups, or this clustering, is one of the basic machine learning tasks. So there's so many other tasks which build upon these latent variable models. One of the exciting kind of areas of research has been these topic models, or models for text analysis. So you can think of like a corpus of documents. So maybe there are newspaper articles, and then you observe all these words in the document. So just by looking at what these documents talk about, what are the words in this document, can I infer what the topics are? So this is again the challenging setting where we don't have annotations of what these documents are talking about, but we'd like to infer them just by looking at which words occur together. And through that process, carry out summarization of these documents. So topic modeling is another application that I'll be covering in detail. So you can think of latent variables in so many other contexts. When you think of social network analysis, again, there are so many things that are hidden from us that we'd like to infer. One of the basic tasks is to understand about how human communities form, both offline and online communities, how people interact with one another, how do they form these groups, and how are these groups related to different interests of the actors involved. And so we'd like to think about finding about these groups directly from graph data. So if I'm given a graph which represents social ties, so these could be like friendships or co-authorships. So these are different relationships between the actors in the network. Can I infer what the communities or the groups that people belong to? So again, these are the hidden variables in the social network model. So you can also think of latent variable modeling for this popular task of recommender systems. I mean, you saw the talk in the morning was all about recommender systems. A probabilistic way to think about it is, that each user has a set of unknown preferences or unknown interests, right? And at the product side, there are different unknown or latent attributes of the products. So how do I infer these latent variables? And using them, I can give better recommendations to the users. So this is a probabilistic viewpoint of recommender systems. So latent variables are also ubiquitous if you think about feature learning or feature modeling. So I'm sure everybody here has heard about deep learning And kind of the basic notion there is to obtain good features from data and then use it for tasks such as classification. Right? If I have a set of images, I'd like to classify them into different categories. I'd like to first extract useful features and then use them for classification. Similarly, you could think of speech or so many other kinds of signals. And here, the framework is to, what are these features? These features are some nice representation of data, right? So they are a nice transformation of data on which you can hope to get good classification performance. So these could be in terms of like sparse representation or incorporating some low-dimensional structures. So again, there is a probabilistic viewpoint of these representation in that there is a underlying probabilistic model with some hidden variables, and by inferring about this latent variable model, I can get better features for my classification task. And computational biology is just another domain where latent variable models can be very relevant. I mean, you can think of so many instances which are hidden or unknown, and we'd like to infer from the data. So one example application is inferring about gene regulatory mechanisms. So this is a challenging task where we are yet to understand how the genes are regulated through a set of mechanisms. And if I only observed gene expression levels of different genes, by looking at these correlations and relationships between these different genes, can I infer something about the regulatory mechanisms? So here the hidden variables would be these regulatory mechanisms. Right? So in all these just example applications, what we see are latent variables or hidden effects. And we'd like to be able to learn them efficiently from data and at the same time incorporate the probabilistic model for learning. So in this talk today, I'll talk about just the basic approach that I which is the clustering approach. So here you can think of each hidden variable as just being a categorical variable. Right? In the basic framework, it is just a mixture of these different distributions. For instance, the simplest setting is just the Gaussian mixture. And a more advanced framework would be to come up with a general probabilistic model where we have a set of hidden variables, we have a set of observed variables, and there are some relationships between these hidden and observed variables. So how do we learn this class of models is something that I'll talk about tomorrow. So today, we'll be focusing on this basic approach that there is this one hidden variable, which is a categorical variable. So this represents the different clusters or groups that the data points are drawn from, and how do I employ these spectral methods for learning. Okay, so, and again, at any point of time, feel free to interrupt me if you have any questions. I'd like to keep the talk as interactive as possible. Yeah, so what are the challenges when we want to think about learning latent variable models? So in all the tasks that I mentioned, the challenging aspect is that it's unsupervised learning. So mostly we do not have access to labels in these tasks. Right? In the basic clustering framework, it means that during training, I do not have access to what the clusters are, like what are the clusters that these data points belong to. All I have is just the samples, and I'd like to learn about the model as well as infer about the different categories, which is the task of clustering the data. So the aspect that it's unsupervised makes it more challenging compared to supervised learning tasks. And when it comes to a model with hidden variables, the very basic question we'd like to ask in a statistical sense is identifiability. I mean, can I even hope to identify these parameters given even infinite amounts of data and computation? Right? So this is the question of identifiability. I mean, not all models are identifiable. So we'd like to come up with a class of well-posed models that can be identified, given that we have infinite data and computation. Right? So usually, like statistical analysis stops at identifiability. Then, but the question is, we'd like to ask whether there are tractable algorithms for learning as well. So whether we have algorithms with small amount of computational complexity as well as sample complexity, right? So whether I can learn these models using, which can scale up to large amounts of data, but at the same time, the number of variables in my model compared to the number of samples is not a terrible scaling. Like I need few samples compared to the dimensionality of the space I want to learn. So this is what I mean by having a learning method with efficient computational and sample complexity. And the challenge is, if you ask about the maximum likelihood estimation, which is the optimal estimation for latent variable models, that's a NP-hard problem, right? So this is computationally not tractable to do maximum likelihood. And the usual methods that people think of for running when there is a latent variable model is expectation maximization or some form of variational Bayes. But they do not come with consistency guarantees. So you only converge to a local optimum that may be very far from the actual global optimal solution. So the question is, can we come up with alternative techniques that have low computational and sample complexities for learning, for unsupervised learning of latent variable models? And that's what this talk will cover, can show that with spectral methods we can learn a wide range of latent variable models. We show that they are efficient in terms of computational and sample complexities, and at the same time, they can be parallelized, they can be scaled up to large amounts of.
Regarding EM and maximum likelihood, finding the maximum likelihood might not be exactly the global optimal might not be exactly the best way, since we have one component that has only one data assigned to it, and that have a very, very high concentration, which will lead to a very large likelihood of that to sort of degeneracy case.
Right. There are also degenerate issue, right? So that kind of also goes to the point of like whether I can even identify the model. And with finite samples, there are indeed the issues of like whether I can even get to the different components. So there are definitely those issues. But even with those, right? I mean, even if I had like say a large enough number of samples that I can hope to get to these different components, the maximum likelihood solution is still hard to compute. So I don't know if that answers your question. And in the spectral method, think of it as an alternative mechanism where we can get consistency results, we can get the estimate of the parameters consistently, and at the same time being able to do it with tractable amounts of computation. And so that's what the series will talk about. So let's start with the plan for this series. So today I'll start with the basics. So perhaps the most basic latent variable model is the Gaussian mixtures. So I'll start with this, and then I'll also start with perhaps the most basic spectral method, which is the PCA, right, or the principal components analysis. So I'll start with kind of the basics of eigen analysis to make sure everybody's on the same page. And once we get through these basics, I want to pose the question that if I have higher order moments, can I have how much more informative is it for learning, right? What more can I learn with higher order moments? So what more can I do beyond the basic PCA? Right? And what we'll see is that there are natural extensions of PCA to tensors. So if I think of higher order moments, you think of them as like multi-dimensional arrays, right? So pairwise moments or correlations can be represented through matrices. And now if I have higher order moments, you need higher dimensional arrays to represent them. At its most basic sense, they can be thought of as tensors. And then we'll see how to think of the spectral decomposition of these tensors, which is the notion of PCA extensions to tensors. So I'll be covering that, and I'll exhibit today that how by doing decomposition on these tensors, we can learn these Gaussian mixtures efficiently. And depending on the time, I'll also talk about these topic models that I described, in the second application that I had. That, so these are models for how topics generate words in a document, and a basic form of topic model I'll introduce today and show that it kind of the moments of that distribution share a lot of commonalities with the Gaussian mixtures. They seem very different, right? This topic models is a discrete distribution, whereas Gaussian mixture is continuous, but they share a lot of commonalities in terms of how their moments are represented. So there is one unified tensor method for learning both these models. And that's kind of the nice aspect of these tensor methods, that they're broadly applicable to a range of different models, and you can see them in a unified viewpoint. And so that'll be for today. Tomorrow I'll be introducing these other latent variable models that I described. These include the community models, that how people in a social network connect with one another. They include the more advanced graphical model, including the latent Dirichlet allocation, and independent component analysis. So there's a range of different latent variable models where we'll show that these tensor methods are applicable. And today I'll be just mostly describing the tensor method, but tomorrow will be kind of the more heavy machinery of how we can go about analyzing these methods, right? How do we establish that these methods provably recover the parameters? So that'll be for tomorrow. And on Wednesday, I'm giving a 1-hour lecture in the morning, and there I'll talk about the implementation details. We've done implementation on single workstation, on GPUs, as well as now a cloud-based implementation on Reef. I think the lecture after me will be covering Reef, and there is a whole set of tutorials on Reef. And I'll be talking about our experiences in implementing the tensor methods on Reef. So that's kind of the whole game plan of these set of talks. Okay, so now let us, just as a pointer, the resources like for the talks, including the slides, there are some simple code snippets that I will show that are available on this website. And the two main papers that I'll cover today, the first one is when I got into spectral methods. So this was the first paper with Daniel Xu and Shyam Kakade when I visited Microsoft Research. And this was the first paper that appeared in Code 2012. And the second paper that I'll be touching upon is this tensor methods for various latent variable models. And in that round, Gilly and Matheus were also involved when they were summer interns at Microsoft Research when I was visiting. So yeah, so these are the resources for today's talk. So let's now begin with the basic PCA methods, which I think many of you are aware. So how many of you are comfortable with PCA and eigen analysis? Okay, so that's almost everybody. So then we can go through very quickly with this and go to the more advanced material. But I just wanted to make sure that we start with the basics. Yeah, so as most of you are aware, the task of principal component analysis is to find optimal projections of my data points such that the error is minimized, right? I mean, it's usually the square error or the square loss we consider. So xi here are the data points. I'll assume that they are centered, so they're mean 0. And I want to find a projection that minimizes the loss. And usually we fix the rank of the projection or the dimension of the projection. And throughout this talk and the coming talks, I'll take that to be k. So k is the rank of this projection. So if you want to do this optimization problem, it turns out that you can solve it efficiently. Right? So first of all, this is a non-convex problem, right, because of this rank constraint. So, but kind of the usual light bulb is, oh, it's a non-convex problem. It may not, there may not be an efficient way to solve it. But for PCA, it turns out that there is an efficient solution, and that's the eigenvectors themselves. So if S is the covariance matrix of my data points, and if I just take the top k eigenvectors, So here I'm going to use U to be the set of eigenvectors. Lambda is the diagonal matrix with the eigenvalues. So the projection will be just to the span of the top k eigenvectors. Right? So that is the optimal projection. So this is the basic PCA result. So let's just very quickly go through why this result is true. So there is the Pythagoras theorem, which means that this loss function can be decomposed into the norm of the signals minus the the norm of the projected points. So minimizing this loss function is equivalent to maximizing the projection of the projected signal of my data points. Right? So that's kind of intuitive to see. And once I want to do this maximization, this is just some simple linear algebra to rewrite it as trace of the projected covariance matrix. Right? I mean, here I've assumed centered points. That's why this expectation of xi transpose is just this covariance matrix S. Okay, so I'd like to be able to maximize this. I'd like to find a projection matrix P that maximizes this trace, right? Trace of P, S, P transpose. So now, again, let's quickly recap why this is true, like why the optimal projection is given by this set of eigenvectors, the top k eigenvector. Right? So this is, again, we know that if it's a symmetric matrix S, it always has an eigen decomposition that is of the form lambda I, ui transpose, where the different ui's or the different eigenvectors are orthogonal to one another. Right? For a symmetric matrix, we have the orthogonality, and we also have this fixed point characterization, where if I take S times U, I still get back U. Right? So if I hit the matrix S with this vector U, I do not move, so it's like a stationary point. And lambda is the scaling, that's the eigenvalue. Right? So this is the basic eigen analysis. And I'd also like to remind you about the Rayleigh quotient formulation, which can be viewed as an optimization viewpoint of these eigenvectors. So the result is that if I wanted to ask for the maximum quadratic form, so the quadratic form is the form when I take a vector z and I take z transpose as z. Right? So this is called a quadratic form because it's quadratic in z. And if I want to find the maximum quadratic form subject to a sphere constraint, that is, I have like all these vectors with L2 norm equal to 1, it turns out that the maximum value is just the top eigenvalue. Right? So again, by convention, we'll be always ordering the eigenvalues from lambda 1 through lambda d, like lambda 1 is the top one. So the Rayleigh quotient result says that my maximum Rayleigh quotient is given by the top eigenvalue, and the maximizing vector is the top eigenvector. Right? So we have now an optimization view of this eigenvector as maximizing the quadratic form. And the minimum one corresponds to the lowest eigenvector. And the PCA result that I described in the previous slide, where we argue that the optimal projection is limited to the span of the top k eigenvectors, you can think of it as the extension of this Rayleigh quotient result to multidimensional subspaces. So this is just like one-dimensional subspace because I'm just looking at a vector, whereas here I'm looking at now a subspace with fixed rank k. And again, intuitively, you can see that it'd be maximizing this trace or maximizing the energy in this subspace if I limit to the top k eigenvectors, right? Because they have the most of the eigenvalue. Yeah. And the value is given by the sum of these eigenvalues. So is this result clear? So this is the just the basic PCA result, but I thought that it would be good to start from here. Right, so we've, I mean, PCA is like probably the first thing you do is when you start with some data, right? You get some data, you want to like first denoise it by projecting it to a certain lower dimensional subspace. Usually K is something that maybe you fix in practice, or you do cross-validation, decide what is the optimal dimension of the subspace to project onto. So this is the basic denoising method. But how do we employ it for, say, this clustering, right? So as I said, I'll start with just the basic Gaussian mixture. So let's see how we can employ the PCA to learn something about the Gaussian mixture, right? So let's see what it is. So again, I'll set up the notation that I will be employing throughout this talk series. So X is my sample, and again, as I said, K is the number of Gaussian components. So it's the dimensionality of my hidden variable. So here H is a categorical variable with K states. And I'm going to use a basis representation for H. So I'm going to use one of the basis vectors. So E1 is a basis vector along the first direction. Similarly, K is the kth direction. So it takes values one of these K basis vectors. Right? So this is just an alternative way to represent categorical variables. And this expectation of H is nothing but the probability of H taking these different states. And that I'll be representing with this vector W. And because it's a Gaussian mixture, we have a different mean in each of the components. I'm just going to collect all of them in this matrix A. So each column of this matrix is the mean for a different component. Right? There are K components, so there is the K columns here. And these data points are d-dimensional. So X is d-dimensional. So I'm observing these points in d-dimensional space, and there are K unknown components. Right? I mean, in this example, it's 2D, so there are, D is 2, and then K is 3. Right? But this is, in general, this could be in higher dimensional spaces. And I'll be mostly limiting to this spherical Gaussian case. So here, so they have some unknown means for different components, but they have the same variance, and it's spherical. I mean, you could extend most of these results to when the variance is different for different components, but it's still spherical. And learning general Gaussian mixtures with general means and variances is still an open problem. So we'll be limiting to the spherical case. And I can make some comments later on where it is challenging to remove the sphericity assumption. And so let's see. So once we have this Gaussian mixture, one of the simplest moments, of course, the first moment is just the mean, right? So this is just like the average of the means of the components. So that's my first moment, or the first order moment of my distribution. The second order moment, I can look at the covariance matrix, right? So that's the next natural thing to look at. And this one, I can write it in this form. So what is the intuition of obtaining this form? Again, you can say, first you can condition this on H, right? On the fact which component it is drawn from. And for each of the components, then I have, so I can, essentially decouple it into these two forms, right? So I can just substitute my X as this mean plus the, zero mean spherical noise. And if I substitute it here, I have these two parts. Because Z is zero mean, the cross term is 0. And here H is categorical, so I know that it is just this mixture of these K components. And then I have this just spherical noise here, the covariance of the noise. So we have this matrix here. So now let's see what happens if I did PCA on this. Right? So the first thing to note is that this is a PSD matrix, right? Because these weights are non-zero, and then I have these rank 1 matrices. And but on the other hand, they are linearly dependent because I have that, so if you just take like this sum, you see that it is 0, right? So that's because I've centered them. So it turns out that if I did a PCA on this matrix, came up to like k minus 1th rank, and then I also take the mean vector, I would get the span of all my component vectors. Because, right, so because I have these, because after that, this is just like the spherical noise, so I'm only going to be shifting the eigenvalues, but I'm going to have the same eigenvectors whenever I have an identity matrix. So by doing the PCA, I can obtain the span of these vectors, along with, because of the centering I have that it's, rank 1 less than k, but when I also take the mean vector, I get the span of my components here. And again, if I took the lowest eigenvalue of the covariance matrix, that's again equal to sigma squared, right? Because these only lie in the top eigenspace, and if I took the lowest eigenvector, I only have this component that corresponds to sigma squared. So by doing PCA, I can get the span of my mean vectors, right, of different components, and I can also calculate what the variance is. Right, so from here, can I now actually learn what the set of mean vectors are? Right, so that's the next question. So is this clear? So we can, because I have this covariance matrix, and I know that it's of this form, by doing PCA, I can get up to the span of my component vectors. Right, and I can also calculate what the variance is of my spherical noise.
But you still don't capture the rotation, right?
Exactly, right? So that's why I haven't said we have been able to learn A. I've only claimed that I can get up to the span of these mean vectors, and I can get the variance. So now we have to see how to do further. But is it clear so far? So PCA does help us something. We can get up to the span. But now how do I do further? This again, I'm sure you've seen before. This is the notion of spectral clustering. Right? So once I'm in the span of these vectors, I can do like k-means or any kind of clustering. Right? So any kind of distance-based clustering. I can kind of, try to find like the centers and then minimize the distance to these centers. So I can kind of, use a range of different clustering methods to do clustering. But the strength of this is because I've done PCA first, I've obtained the span of my mean vectors, I can reduce the noise, right? So I'm much better off doing this clustering on the span of my set of unknown vectors A, right, which form this matrix A, rather than in the ambient dimensional space. And this is especially effective when the dimensionality of my space D is much larger than the number of components. Right? If there are only, say, like a few components in a very high dimensional space, if I try to directly cluster there, I would be encountering a lot of noise. But if I did PCA, then I kind of, get to the subspace where I know the mean vectors lie, right, up to some perturbation, and then I can cluster in this space. Right? And you can kind of see it being represented by this figure. That, I can try to find like the separate, if there are two components, like what is the separating hyperplane that divides these two components, right? And there has been so I won't be covering in detail about spectral clustering. There is an entire series of works that talks about the guarantees for learning through these clustering methods. So the idea is, do PCA. You can even do PCA on just the data matrix itself. I showed it through the covariance matrix because I'll be exhibiting like other moment-based estimation later on. So you get the span of these mean vectors. You just do clustering on top of that. But what is the downside of these methods? So the downside is if you have a large amount of variance or a large amount of noise, you will fail in clustering correctly. Right? So the clustering only works if the separation between my means is sufficiently large compared to my variance. Right? If that is not the case, then I'll be failing to cluster correctly. I'll make a lot of errors in asking where these data points come from, right? What are the components that these data points belong to? And once I fail to cluster, I won't be able to learn either, right? Because this hinges upon the fact that first I cluster or classify the points, and once I classify, I can learn the individual means. But if I'm unable to cluster them, then I cannot learn the components. So the question we want to ask is, without having these separation constraints, even in this challenging case, right, where there is very little separation between these different mean vectors, can I still learn them? And what are the techniques for doing that? And that's where these tensor techniques will come up. So is the point clear? Yeah, so that's the question. So how do we learn these, even in the simple case of Gaussian mixtures, the mean components without assuming any of these separation constraints? And we saw that the PCA, looked at the covariance matrix. If I now incorporated higher order moments, can I do better, right? So can I get more information? Intuitively, there should be more information in higher order moments. Right? Unless the distribution itself is Gaussian, then just mean and covariance is sufficient to describe it. But because it's a mixture of Gaussians, the higher order moments have more information. But the question is, how do we use it efficiently for learning? Right? And there are also other settings where it would be useful to have higher order moments. So what if I have the number of components of my Gaussian to be larger than the dimension itself? Right? For instance, a lot of Gaussians in one dimension. Right? So in this case, the PCA is not, it does nothing. Right? So naturally, you would think that higher order moments would be very important, in fact, crucial to learn over-complete models. And tomorrow I probably won't have time to go in detail, but I'll be touching upon how tensor methods are applicable for learning over-complete models. So when I say over-complete, I mean that the dimensionality of my latent space is larger than the dimensionality of my observed space. So here it's the number of Gaussian components being larger than the dimensionality of the data points. So this is another important setting where higher order moments are useful. And of course, I gave you a set of applications where the data is very far from Gaussian, right? So we have this whole range of different probabilistic models, and there, how do these higher order moments help? So there are, a lot of very crucial points where, there is good reason to go beyond the basic PCA. So how do we now go to, yeah?
So going back to a point about different cluster variants for different variances for different clusters. If the span of your centers is less than d-1, such as less than k-1.
Right. So if it's rank deficient, you mean?
Sorry.
If it's rank deficient, you mean?
Right. Yeah. Then do you run into problems if
yes. I mean, right. So that's kind of also, that's also an identifiability question, right? I mean, you could have in the trivial case just two columns being exactly the same. If they have exactly the same mean, then there should be just one component and not two. So once you have that issue, then you also have to question on what I mean by non-degeneracy and identifiability. So that goes back to my question of whether the model is even identifiable. Right, and in the case when there is rank deficiency, it's you wouldn't be able to identify it beyond the span, beyond just getting the span of those components, unless you have more information. And potentially the higher order moments can help there as well, right? So, but just with PCA you cannot do beyond, right? Okay. Any other questions? Yeah, so the question is, how can we go beyond the PCA and what do these higher order moments mean? Yeah, so let's see for Gaussian mixtures, how do these higher order moments look like? Yeah, so where do these tensors come up? So if you think about a higher order moment, now you have to use multi-dimensional arrays to represent them. For instance, we saw that when we were looking at correlations or covariances, they are represented through matrices for multivariate distributions, right? For a d-dimensional mixture of Gaussians, so now the covariance is a d by d matrix. Now, if I want to have a tensor, right, so it's now the third order moment of my d-dimensional Gaussian mixture, I have a d by d by d array. Right, so think of it, the matrix, I can represent them as rows and columns. The tensor, now the third order, I can represent it as a three-dimensional cube. I mean, of course, fourth order, you can't physically represent it, but you can, imagine, right? So that's kind of the first way to think about the extension. We'll now put down some conventions of how to represent it. So for matrices, I'm going to use this notation that x, this chronicle times x, right? So this is an outer product of this vector x. So for matrices, this is nothing but similar to just taking x transpose. Because the convention is if I wanted this outer product and I asked for now the I1th row and then I2th column, that is nothing but looking at the moment between the I1th dimension and the I2th dimension. Right? So this is the indexing convention that if I take the this matrix and I ask for the I1, I2th entry, that represents the correlation between the dimension corresponding to I1 and I2. And similarly, now we can extend it to the third order case, where if I wanted the third order correlation between dimensions I1 and I2 and I3, right? That's the sphere, that I will represent it with a block here, like in this cube. Okay, so I have like I1, I2, I3. I just have the indices for the three dimensions in my tensor. So this is the convention, and I'm going to use this notation for representing the tensor product or the outer product of a vector, either with itself or with others. Right? So this is the second order moment. This is the third order moment. Is the extension clear? Right? Because it's multivariate, I now have this three-dimensional array for representing the moments between all three dimensions. Right? So that's what these indices represent. Okay, so now that I have the notation pinned down for representing my third order moments, let's see what they are for the Gaussian mixture. So as I said before, right, so we want to look at now, we have like this mixture of k Gaussians. So my data point is like mean plus spherical noise. And if I want to do the third order tensor, it's again a very similar operation as we did with the covariance matrix. So for x, I have the mean term, which is a times h, right? So it's one of the mean components, and then there is the zero mean noise, which is z. And if I just expand it out, there are only some subset of terms that survive. Because I know that z is zero mean Gaussian, this third order moment is zero. Right? So expectation of z times z outer product is zero. So that term doesn't survive. And similarly, the term that has only one z, right? So also doesn't survive because it's again mean zero. So these are the only terms that survive that kind of have the second order term in the noise, right? In z. And so these are the two terms. So that's why you have this first term that just corresponds to the means themselves. Right? So the idea is with probability Wi, I pick the mean to be AR, right? This vector AR. And so its third order moment is just AI, tensor, AI, tensor, AI. And it's a mixture of this. Is that clear to everybody? Why that comes up? Because this is the notion of a mixture model that if this category was I, right? That happens with probability Wi. The mean would be just AI. Right, so this is a pretty crucial notation. So if you have any questions here, this would be the right time to ask. Is that clear to everybody? So you obtain a component that corresponds to just the mean vectors, right? So it's the outer product of like the different mean vectors, the AIs. And then there is a component that corresponds to the variance term, right? And because with spherical, we know that in each direction the variance is sigma squared, right? So this is EI is now a basis vector. Because it's identity, I can represent it as EI times EI, right? Plus the summation of them over all the dimensions. And that's why, and this is just the mean, which is always equal to mu. Right, so this is the mean of the Gaussian mixture, and so that's how you get this, higher order moment of this Gaussian mixture. So I just kind of went into the details of how to compute this because tomorrow we'll be seeing a lot of other latent variable models, and I won't be going into details there. But at least in the simple case, you can see that if I wanted to compute the third order moment of a multivariate Gaussian mixture, you can kind of break it down into these simple terms, and then they have very simple ways to express. Right, so and here we have used the fact that it's a spherical Gaussian, because in that case it's just sigma square in all the directions. That's why you only have these basis vectors, and it's just sum of these over these basis vectors. So that's where the spherical assumption comes into play. So once we have this form for the Gaussian mixture, the question is, how can I exploit it to learn my parameters? So I want to learn the vector of means, which is this matrix A, and the weights W, which is the probabilities of different components. Right? So how do I learn from this? So if you recall, we were able to obtain the variance, right? The sigma square from PCA, like from the lowest singular value of my covariance matrix, I can obtain what sigma square is. And I also have the second order moment. So just by looking at the correlation, I have like the mean vectors and also this variance term. So I can cancel out the sigma square term, and even here I can remove the sigma square term. So in the end, I can reduce it to a form where I just have these M3 and M2. I mean, these are just functions only of the unknown parameters, right? The matrix A and the weights W. So I've removed all my known parameters, which is like, earlier there was this mean mu, right, of the Gaussian mixture. There was the sigma square, there was the variance. So I just was able to get rid of all the terms that are already known. And now I've reduced it to a more compact form that only is a set of equations that relate the unknown weights and the mean vectors. Right, so how do I describe this? These are, trilinear and bilinear forms in the mean vectors. So these are a mixture of these mean, trilinear forms of these mean vectors. That's the third order moment M3, and the second order moment M2 is a bilinear form of the mean vectors. Right, so once I'm given this, now how do I go about learning this? And in fact, why I'm stressing on these two forms is that a range of different other latent variable models can be reduced to the same form. So that's why keep in mind that this form is what we'll be working on throughout our algorithms. And kind of the more, I would say, the trick part of it is to, once you have a latent variable model, is to ask whether I can reduce it to this form. Of course, not every latent variable is reducible, but we'll see a whole range of latent variable models can be reduced to this form. So is it clear? From here on, I mean, the fact that it's Gaussian mixture is less relevant, but now the question is, think of this as a set of equations, right? These are a set of multilinear equations in these AIs, in these unknown vectors AIs, as well as these weights. So now how do I go about learning this? So yeah, so another notation that I'd like to introduce where we'll need is, once I have the tensor, I want to be able to do transformations of the tensor. So think of a tensor as a multilinear operator, right? So what do I mean by that? So I'm going to use this function. So if it's a third order tensor, I can, input any three matrices, right? I mean, they could even be the same one. But I have these matrices B, C, and T, and if I input them, I'm going to do linear transformations of these components of my tensor. Suppose I have this tensor of this form, right? If I now input these matrices, I can do these linear transformations of those set of vectors. So this is again a notation, and you'll see that this notation will be using in a lot of contexts. And an immediate way that I will use it first is to think of reducing a tensor to a matrix. Because I introduced these tensors, but we are still very comfortable with matrices, right? We can do eigendecomposition, we can do a lot of operations just on matrices. So the most naive thing to do probably is to, even though we have a tensor, can I just obtain a matrix from it? And then try to learn my parameters from this matrix. And the matrix that I'm going to obtain can be seen as a slice of this tensor. So what do I mean by that? If I look at this notation of this multilinear operation, I'm going to just input identity for two of the modes. So meaning two of the modes of this tensor, I'm not going to change, right? So they just remain as it is, right? So in this form here. And the third one, I'm going to take a projection along this fixed vector R. Right? So, and this is now a matrix. So that's because, pictorially you can think of it as like this. I'm taking a slice of my tensor. Even though it's a cube, I'm just taking like a two-dimensional plane. Right? And I'm asking what are the values along this plane. So is this notation clear? So now, if I had this operation now, I'm only now taking a slice of the tensor that has this form here. So the idea is that this I can write it in terms of this unknown matrix A and a set of diagonal matrices and A transpose. And even my pairwise moment, I can write it in a very similar form. Right? I mean, if A were orthogonal, this is also known as simultaneous diagonalization problem. Right? Because I want to find like ways to have this form where I have like A, some diagonal matrix times A transpose, and another matrix of the same form. So they only differ in their diagonal matrices, but they, the outer parts are still A. Right? So I have some better structure by doing the slice of a tensor. Right? I mean, earlier if I had only a second order moment, I only had this one matrix here, but now I have a second matrix where it only differs from this diagonal part. The rest of it is similar. So can I now solve these set of equations to obtain A and W? Right? So although I introduce tensors, I'm only taking a slice of tensor and still trying to do some matrix operations to recover the unknown parameters. So yeah, I'll come to that in a minute. So, but for some fixed R, this is the notation. Right? So this is how I obtain a slice of the tensor. So suppose I have these two matrices. Now can I ask how can I obtain A and W? Right? So I know R. And I have the freedom to choose R. Right? So I can choose it in any way I want. So yeah. So that's my set of like two matrices, and I'd like to obtain A and W. So let's for a moment think of the simple case where A is full rank, right? Where the number of components K is equal to D. So if A is itself invertible, M2 is also invertible. So in that simple case, what happens, right? So if I took like M2 inverse times this matrix, right? So what do I obtain? I obtain A times some diagonal times A inverse. Right? Because this part, the middle part kind of just cancels out. So if you just do the math there. So, in the case of the full rank setting, I have this decomposition as A times the diagonal matrix times A inverse, and this is nothing but an eigen decomposition. Right? So, but now I don't have this full rank. In general, K could be less than D. So we will be, almost throughout this talk and the next one, making the assumption that these are latent variable models where the dimension D is bigger than K, or K is at most D. So meaning that this matrix A has full column rank. Right? So this is kind of again a non-degeneracy assumption that will be needed for learning. And indeed, it is possible to learn even without this assumption, but in general, that's a NP-hard problem. So, but we'll see that under this assumption, we'll obtain tractability. So suppose A has full column rank, then we don't, so we still want to be able to do like an eigen decomposition that I described, right? But it's no longer full rank, it's not rank D, but what I'm going to do is I'm going to reduce them to like K by K matrices, and then do decomposition in that space. So how do I do that? I'm going to first do an eigen decomposition of my second order moment. And then I'm going to project it onto this K-dimensional space. Right? So if U lambda U transpose is the eigen decomposition of my second order moment, then I know that U transpose M2 U is invertible. Right? Under the assumption this is rank K. Right? So if A is full column rank, and the weights W are all non-zero, I know that the second order moment has rank K. So I have now this being invertible, right? So I can just change my argument to now taking the inverse of this. So I'm also going to project my third order moment, the slice of my third order moment, also to this, this span of U. And so essentially the idea is now I have these two matrices. I want to find its eigen decomposition. So this you can compute again tractably. And so how do I, once I have this eigen decomposition, so I can find V and this diagonal lambda tilde V inverse. Right? So I can find this eigen decomposition. From this, how do I find my parameters A and W? So that's, I can see this by doing the substitution. So this corresponding product is the same as, projecting A onto this U. So that is U transpose A times a diagonal matrix times its inverse. And so what we see here is up to scaling, we have that these columns VI are proportional to U transpose AI. Right? But that's where, this is under the assumption that I have an eigengap. Right? So this is under the assumption that this lambda tildes are separated. So otherwise, I wouldn't be able to get to the individual vectors. Right? So if I had an eigengap between the different lambda tildes, then I can have that these VIs are essentially projected AIs up to scaling. Is this clear? It's a bit involved, but kind of the main message I want to say is to think of like finding an eigen decomposition of taking these two matrices together. I'm essentially taking the inverse of the second matrix times the first one, but I'm projecting them to K-dimensional matrices because then it becomes invertible. Otherwise, they're not invertible by themselves. Right? So this is just kind of a way to, if they were full rank, you could have just directly taken their inverse. And so this is the eigen decomposition. And what we show is when there is an eigen gap, you do get these AIs up to the scaling. Right? So, but now the question is, how do I get the scale as well? Is that clear? So we've taken these two slices, and so if I don't care about the scale, I can just say that the mean vectors are up to scale just like U times these VIs. right? So I can get from these eigenvectors my component means, but up to the scale. Okay, but if I also want the scale, it's a bit more involved. I mean, I won't describe it in too much detail here. You'd have to take many different slices. You'd have to kind of collect all these eigenvalues together, and you'd have to compute this overall equation. So it's also possible to recover the scale, but let me not go into the detail of that here. But the main message here is if I had like two slices, right? So, sorry, a slice of my third order moment and as well as my second order moment, by finding an eigen decomposition, I can recover the mean vectors as well as the weights. Any questions? So the thing is, with just the second order moments, we could only recover the span of my mean vectors. But by just looking at the slice of my third order moment, we can now recover the matrix A as well as the weight stability. Right? I mean, of course, once you recover A, it's trivial to recover the weights. Right? So this is kind of the idea that with eigen decomposition, I can recover the components of my Gaussian. And so this was our first paper that we realized by looking at higher order moment, we can now actually recover the parameters of my Gaussian mixture. Right? So this is nice conceptually. This gives a guaranteed way to recover the parameters. But then in practice, there are a lot of issues that are not so nice. So the very first thing is that we have to compute this eigen decomposition, which in general may not be an orthonormal set of eigenvectors. Right? Because if you notice this product here, this may not be a symmetric matrix. Right? So only for symmetric matrices, I have the eigen decomposition being an orthonormal system. But if it's not symmetric in general, this is not orthogonal. And the algorithms for that are more involved than doing the usual symmetric eigen decomposition. So that's one algorithmic aspect. And the other also very important thing in practice is how to obtain these tensor slices with good eigengap. Right? So this was a question that was asked. I mean, because kind of the whole recovery hinges on the fact that I have good eigengap. Right? Only then I can separate out these different components and I get these different mean vectors. So I can only have this when, in practice, I don't know how to find these good slices. And if I did like random slices, right, then the eigengap is very small. So as I increase the number of components, the gap shrinks polynomial. And this is not just a theoretical notion. Even in practice, I have numerical instability. Because I'm taking this random slice of this tensor, and then I'm kind of trying to find its eigen decomposition that's not so stable in practice. So this was kind of the main drawback of this, that although I have this tensor, I'm taking random slices of this tensor. Right? So this does not seem like an efficient method to exploit my information in the tensor. So are there other ways to do the decomposition of this tensor or to recover the parameters without taking these slices? Right? So that's kind of the whole message of this part, that I went to these higher order moments, I obtained this third order moment, but I'm only still reducing them to matrices. So I'm still doing matrix operations because I'm taking slices of this tensor. So can I do better by directly looking at the tensor itself and trying to obtain the parameters? So that's what the next part of the talk will be about, in saying why, although conceptually this eigen decomposition is a way to recover the parameters, in practice and also in theory, it's much more powerful to directly look at the tensor and ask how we can find efficient ways to learn the parameters from the tensor. Yeah.
Is it also possible to think of this conceptually as clustering by students in each component?
So this is, I would say it's conceptually different from clustering because we are not trying to classify the points. So we are not inferring what the groups different points belong to. So we are directly learning the parameters. So think of it as like a moment-based estimation. I'm looking at the moments as a set of equations and I'm trying to invert them. Right? So in that, and that's why the settings where the clustering methods will fail, where there is not enough separation, these methods can still separate. And that's the fundamental difference between the two. But the main idea is from the third order moments, what are the set of equations we can solve tractably? Right? Because you could write down the equations, but they may not be computationally efficient to solve. And what is shown is by reducing this tensor to matrices through slicing, we can do an eigen decomposition, which is again tractable. So we have a guaranteed way to recover the parameters, but it's not so efficient. So the question is, can we improve upon this? Okay, so that's what we'll see now in the next part of the talk. And this I would call it as a tensor factorization method, because now we're going to directly work on the tensor and see how we can obtain the components. Right, so to recap, we have the second order moment, which is a bilinear form in these unknown mean vectors AIs, and a trilinear form of these vectors AIs. Right, so I can just directly look at this third order moment and ask, what does this mean? Right, so I want to find a decomposition of my third order moment into these terms. Right, so each of the terms, the first term is W1 times A1, auto product A1, A1. The second one is W2 times, and so on. Right, so what do each of these terms represent? These are rank 1 terms. Right, so what do I mean by a rank 1 tensor? Right, so if you recall the notation, if I had a tensor of this form, right, A tensor A tensor A, and I asked for its entry corresponding to I1, I2, I3, right, because this is a third order tensor, I have like 3 indices here. And these are directly obtained by indexing the corresponding entries of the vector itself. So that's what I mean by a rank 1 tensor. Right, so for a rank 1 tensor, if I wanted an entry in any location, all I need to do is look at the corresponding entries of the vector itself. Right, and here I made it symmetric. In general, it could be different things, A, B, C. Right, then you kind of query what are the corresponding entries of those vectors. So that's the notion of a rank 1 tensor, which is very similar to a rank 1 matrix. Right, so for a matrix, it would be A transpose. Right, and even there, if you had to query an entry of that matrix, you would just query the corresponding entries of just the vectors themselves. So think of it as just the extension now to this third order tensor, the notion of rank. And now what we require is the decomposition of this the given tensor M3 into k components. Right, so this is a decomposition of the tensor. Right, so I can now directly ask, how do I find this decomposition? Right, so again, do you see parallels to like SVD? Right, for a matrix, if I wanted like a rank k decomposition, I can write it as sum of rank 1 components. And here again, it's the same question, but for tensors. How do I write a tensor as sum of rank 1 components? Right, if I had a method to be able to find me this decomposition, then I can relate them to these terms in, which are the different mean vectors of the components. So here immediately there are 2 questions that come up. So first the question is, if I ask for the most compact rank 1 representation of my tensor, right? So the one question is, can I express my tensor as the minimum sum of rank 1 components? Right, and that is known as the CP decomposition, or the Kandikov means like canonical decomposition, Parafac is parallel factors. I mean, these are classical terms, but the problem is, given a tensor, I want to find the minimum number of rank 1 components that make up this tensor. Right, so I want to express the tensor as sum of rank 1 components. So suppose I were to do this CP decomposition, the question is, when does it correspond directly to these components of my means? Right? Because this is true only when this is the most compact representation. Otherwise, they may be different. Right? And then the question is the algorithm, of course. Right? How do I actually find it? So is it clear? There are two problems here. So one is, I've defined this concept of a CP decomposition. So I have a tensor. I want to find the minimum number of rank 1 terms. And suppose I find this rank 1 terms, when do they actually correspond to the mean vectors? So this is again a notion of like a non-degeneracy that I don't want as, given these mean vectors, a smaller number of terms representing the same tensor. Right? And then the second is, of course, how do I find it efficiently? Yeah.
How do you know the K-term representation of MC?
Sorry, I can't hear you.
How do you know the K-term representation of M3 is the smallest?
So I want to find this. That's the question I'm posing.
Yeah, is it possible to have like K-1?
And that's the identifiability question, right? First of all, when is the rank actually K, right? So if I think of this rank as the minimum number of rank 1 terms that make up this tensor, when is it actually equal to K? And that is exactly this identifiability question. When do I have that property? And then the second is, how do I find this? And that's what we'll be addressing now for these questions. Okay, so these are now inherently tensor operations, right? Before that, what you saw was just taking a slice of the tensor and still, doing operations on the matrices. But now we are just directly looking at the tensor and asking, can I find these rank 1 decompositions, and when do they correspond to my mean vectors? Yeah, so let's now take a very simple case, get some intuitions, and then see how we can solve the more general case. So what if, like the mean vectors were actually orthogonal columns, right? So the different means of different components had like 0 inner product, like they were orthogonal. I mean, of course, this is a very limiting case. We want to handle the general case. But let's for a minute just limit to this case. So in this case, what properties do we have? So if you again recall this notion of the multilinear operation that I described, suppose, suppose I input A1, right? I mean, I don't know A1. Suppose I had an input A1, which is the first vector. So it's the mean of the first component, and I did a multilinear operation on 2 of the nodes, meaning that I take this inner product square here times AI, right? So meaning 2 of the modes I hit along A1, right? I project all these terms along A1 here. And then the third one I just keep it as it is. Right, so if I do a multilinear operation on the tensor where 2 of the modes I reduce with a vector, I get back a vector. Right, so this is again a contraction operation on the tensor. And now, because the components are orthogonal to one another, what we see is that the only component that remains is just the component I started with. Right, so this is a fixed point equation for A1, right? So if I input A1, the output is also A1. And this is true for any of the mean components, right? So if you verify any of these components AI, if I input to this quadratic operation here, right, I still get back A1. So this is just a characterization of the components. Right, so I haven't told you how, I don't know A1, right? Because the whole goal is to obtain these components. But suppose I had orthogonal components, what I'm saying is it has this nice fixed point characterization. It's possible to verify, suppose I claim that A1 was one of the components, right? I can verify through this equation. Right, so we obtain that characterization. So in fact, we can view this as eigenvectors of this third order tensor. So why am I thinking of it as eigenvectors? Because again, recall for matrix eigenvectors, right? So here I'm hitting F with this vector V. If I do not go anywhere else, I still remain at V, then it's an eigenvector. And in my multilinear notation, that means in the second mode of my tensor, the second order tensor, which is the matrix, I'm hitting with V here, right? And I'm still remaining at the same vector V, right? I'm not moving. So it's a stationary point of the operation. And here it's a similar notion. The only thing is now it's a nonlinear operation, right? I'm hitting two of the modes with this vector, and I'm still recovering the same vector, right? Because the tensor, now it's a three-dimensional array, I have to contract 2 dimensions of them to obtain a vector. And if I still obtain the same vector as an input, then it's an eigenvector. So we have a fixed point characterization of these components of this tensor when they're orthogonal. Right? So if I had an orthogonal tensor, we know that these different components correspond to eigenvectors. Right? And the definition of an eigenvector is this quadratic operation that I described here. Right? So think of it as like along 2 of the modes of the tensor, I'm projecting along this direction, A1, right? And I recover another vector. And it should be the same vector. Is that clear? So we have an vector characterization of all these components here. So still there are 2 issues. The first issue is that assuming that different mean components are orthogonal is very restrictive, right? So we want to handle the general case. So the question is, how do I still handle the general case, right? Is it possible to convert a general tensor to an orthogonal tensor? So that's one of the questions. And the second is, suppose I had an orthogonal tensor, then I know that my components are eigenvectors of the tensor. But how do I obtain them? What is the algorithm to find these eigenvectors? Right? All I showed was a characterization of what these eigenvectors mean, right? It's the definition. But now, what is the algorithm to find them? So these are the 2 questions. So is it clear? If I had an orthogonal tensor, we have the components are eigenvectors. So the first question we'll ask is, how do I convert a fixed set of vectors which form this matrix A to an orthogonal system? Right? So what is the concept here? So in general, as I said, we do not have these vectors being orthogonal to one another. So what I would like to find is a transformation that makes them orthogonal. Right? So it's a linear transformation. Right? So this is what I'd like to find. I'd like to find a matrix W such that if I apply W to this matrix A, right, the resulting system is orthogonal. Right, so it's a linear transformation, and so once I find this orthogonal system, I can do a decomposition of an orthogonal tensor. But to recover back these components, this should be an invertible transformation. So what I mean is, from A I can obtain V, but also from V I should be able to obtain A. Right, and this is true if again the same assumption I had before, that these mean vectors have full column rank. So again, this rules out those degenerate cases where they may not, like these that they don't have like the full dimensional span, right? So all these the different mean vectors are non-degenerate. So in that case, suppose I were to orthogonalize the system, I can also recover the individual vectors by just inverting the transformation. So now the question is, how do I find this transformation? Right, and just to kind of make it clear, once I had this transformation, what I'm going to do is convert my original tensor, right? So my third order moment tensor to an orthogonal tensor. And I'm also going to reduce dimensionality because I had a d-dimensional tensor. I'm going to reduce it to a k-dimensional tensor where k is the rank, right? So k is the number of components. So that's kind of the true number of parameters. So I'd like to be operating in this k-dimensional space. And that, again, can be done using this linear transformation W. So the idea is, once I obtain this matrix W, I can do a multilinear transformation of my tensor. So earlier I had this M3 as the weight times AI, tensor AI, tensor AI. And now I'm going to, like, for each of these modes of the tensor, I'm going to do a linear transformation, right? So I'm going to have W transpose AI in each of the modes. And that's exactly this notation here, right? And that's exactly here. So I'm taking W transpose AI. So think of it as like now I have a tensor where the different components are orthogonal to one another. Right, so this, I mean, the picture is exactly this. So I have now had an arbitrary set of vectors which had full column rank. I mean, if I had a linear transformation, I could make it an orthogonal system, and then I'm gonna, use this linear transformation along all the modes of the tensor, and this way I can obtain an orthogonal tensor. Okay, and in the process, I'm also going to do dimensionality reduction, which you can think of it as a version of PCA for tensors, right? So I'm also reducing the dimensionality of the space that I'm acting on. And in fact, in practice and also in theory, this is important to reduce the noise. Like with, when I have noise, I want to do the operation in the k-dimensional space. But that's a detail aside. Yeah, so now the question is, how do I find such a transformation W? And this is also called whitening because I can do this by using the pairwise moment. And in fact, it's the matrix that whitens the pairwise moment. Right? By whiten, I mean that W transpose M2 W is an identity matrix. So, so I had like this set of vectors here. I'm going to turn it into a rotation matrix, right? I'm going to turn it into an identity system. And what is the transformation that does it? So this can be easily found by doing SVD, right? So how is that? If I had the decomposition of my second order moment as U times this diagonal times U transpose, I just have to like kind of rescale my diagonals, right? Because I want to make it identity. And you can verify that if I use this form, I can obtain this requirement. I can whiten my second order moment. So by doing an SVD of my second order moments, I can find the transformation that makes the system of these AIs to be an orthonormal system. Okay? And once I have the system, as I said, I'm going to apply it to my third order moment, right? And I'm going to reduce it to a k-cubed tensor. So each dimension of my tensor is a k dimensions, and all the components of my tensor are orthogonal to one another. So is it clear? So we had a general set of components for my third order tensor, but now I reduced it to an orthogonal tensor. And for that, we use the second order moments, and we obtained a whitening matrix to do that. Any questions here? Right, so then the next aspect is, given an orthogonal tensor, how do I go about finding its eigenvectors? Right, because we know that the components form a set of eigenvectors for this tensor. And so this is where we will use the fixed point characterization of the eigenvectors. Because so if you recall, what was this characterization? If I input this one of these vectors, say v1, right, and reduce two of the modes of my tensor, I would still recover the same vector. Right? And when I have a fixed point characterization, perhaps the most naive thing to do is just to run this iteratively, right? So I start with some random vector, right, or any given vector, and then I kind of do this map. I'm going to normalize because the convention is I'm going to have normalized eigenvectors, and then I'm going to just repeat the operation, right? And the hope is it will converge to an eigenvector, right? Eventually it will stop. Because that's the stationary characterization of the eigenvector. And so that's the canonical, recovery method. And in fact, it's, I'm sure most of you know of the matrix power method, right? You have a matrix M, you have a vector, you kind of do M times V, you normalize, and you keep repeating this, and it'll converge to the eigenvector. In fact, it will converge to the top one if you initialize it with some correlation with the top eigenvector. And tomorrow I'll be talking giving all the details about the convergence guarantees. But for today, just think of this as paralleling the matrix power method. So here I have this tensor. I'm going to start with a vector. I'm going to do a quadratic operation on my tensor. I'm going to contract along two of the modes to obtain a vector. I'm going to normalize it, and I'm going to keep repeating this operation. So it's an iterative process, and in the end, I'm going to obtain an eigenvector. Right? And so you can do random initialization if you don't have any other information. Right? Similarly, you would do random initialization with matrix power method. And you run to convergence, and then once you obtain an eigenvector and an eigenvalue, you can deflate. Right? You can remove that component and then start the processing. And this is what is done even in the matrix analysis. Right? So this is kind of the canonical method for recovering eigenvectors. Right? I mean, I haven't yet told you why it succeeds, right? Or in what time it succeeds, and that I'll say tomorrow. But today, kind of the idea is, well, if I had an orthogonal tensor, the components are eigenvectors, and I can find these eigenvectors through this power method. Okay, so that was the entire method. So let's put all this together because there was a lot of different aspects here. Right? So we had a Gaussian mixture here, and we saw that under spherical noise, we could reduce it to having a second order and a third order moment of this form. Right? These were just bilinear and trilinear forms in my mean vectors. Right? These AIs were the means of different components, and I had these two forms. And the basic idea was to first use the pairwise moments to obtain a whitening transformation, to obtain a transforming matrix W that changed my tensor to an orthogonal tensor. Right? So essentially, I applied this linear transformation along each mode of the tensor, which meant I applied this transformation along this set of AIs. And once I had an orthogonal tensor, we saw that the components correspond to the eigenvectors. And I can obtain these eigenvectors through a power method. Right? So where I iteratively substitute my obtained value in the quadratic operation and repeat. And then I'm going to do the deflation and keep repeating this again. And through this, I could obtain the eigenvectors and eigenvalues of my orthogonal tensor. And we saw that they are a linear transformation of my original mean vectors. Right? They're transformed by this matrix W. Because it's an invertible transformation, I can just obtain my original set of vectors here. Right? So this is how I'm able to obtain the mean vectors, and once I obtain that, obtaining the weights is trivial. Right? So this is the overall method. I mean, I still didn't prove that it succeeds. That's what tomorrow is for. But I hope that it's clear now, what the method is doing. Right? So we are looking now at this third order tensor as a whole and doing its decomposition. Right? And that decomposition, we did it in two steps. One was whitening the tensor to obtain an orthogonal form, and then using the tensor power method to find the decomposition of an orthogonal tensor. And once I have that, because it's an invertible transform, I can find the original decomposition. Okay, so this was the overall method. So we could do Gaussian mixtures with this method. So the question is, can we do other latent variable models? So now I'm going to look at topic models, which I described in the right in the beginning of this talk, and see that, in fact, at outset they look very different, right? Gaussian mixture, Gaussian is continuous, whereas this topic models you'll see is a discrete model. but there is a unifying representation, and the moments, in fact, will be exactly of the same form. We can obtain very similar forms as in the Gaussian mixture, so this method just applies as is, even for learning topic models. And tomorrow I will cover a whole new set of models that also can be reduced to this form. So let's see now for how we can, look at the moments of a topic model. Right. So first of all, the notion of a topic model is that there are, words in a document, and I'd like to explain these words through hidden topics. Right. So think of it as, particular document as a sample, and this has a set of words, and these words are drawn from a bag of words model. So the idea is that each document may be a mixture of different topics, right? For instance, politics, science, and so on. And now, given each topic, there is a certain probability of the words being drawn. Right? So there are two aspects that now, for each word, I'm going to draw a topic, and then given the topic, I'm going to draw a word. And through this, I can generate the set of words in my document. And as a graphical model representation, we can think of it as an exchangeable model where this is hidden variable h, which represents the proportions of different topics in the document. Right? And in this talk, I will be just focusing on the simple case where there's only one topic in the document. But tomorrow, we'll handle the general case. So for now, just think of the general case where h could represent proportions of different topics in a document. And to draw each word, first I'm going to draw a topic from this mixture. And then I'm going to draw a word according to some conditional probability table. And similarly, but the thing is, even for the second word, I'm going to do the same thing, so it's an exchangeable model. So that's why it's called a bag of words model, because the order of the words does not matter. So it's only like the occurrence of different words, right? That's the only important thing here. And so we have that, there is this matrix A now represents the conditional probabilities. So what's the probability that the word takes a certain value given that the topic was a certain value? Right? So this is now a D by K matrix if D is the size of the vocabulary, the number of possible words, and K is the number of possible topics. And the observed words are discrete, right? Because they are one of the possible D words. So we have a discrete distribution on the words here. And the exchangeability model is saying that condition on this proportions of these topics, right, this variable h, or the draw of all these words is conditionally independent. And that's kind of where, this makes it a simple model, because I have just, what are the parameters here? One is the this topic word matrix, which says how different words occur under different topics. The other is the distribution of how different topics are distributed in documents, right? What are the values that these topic mixtures take? Okay, so these are the unknown parameters in my topic model. And what is different from the Gaussian mixture? You have many words in the document. So meaning you fix the configuration of h, so you fix what is the state of h, and then you will draw many different words. Right? And that's what I'll call a multi-view model, so I'll come to that in a minute. And so this is again different. Now you have multiple different words conditioned on the same configuration of my hidden variable h. Okay, and because I want to represent this hidden variable h represents the proportions of topics, I'm going to represent it on a simplex, right? It's a distribution on a simplex. Because I want these different coordinates to be positive, right, between 0 and 1, and they should sum up to 1. So it's on a simplex where the vertices are just the basis vectors. So there are k vertices here corresponding to k topics. So if it's only one topic, then h is just a categorical variable, right? Similar to the Gaussian mixture that I described. and then it takes only one of the vertices as the states. Okay, so tomorrow I'll talk about the more general latent Dirichlet allocation, where the distribution of this H may be a Dirichlet distribution on the simplex. But for today, just think of the simple case where each document has just one topic, right? And given this topic, I'm going to draw multiple words from my, the topic word distribution. Okay, so before I get there, just think of like, this is the viewpoint that I like the best to describe the topic model. So this is hidden from me. So this is the distribution of how different topics are distributed in documents, right? So each sample is a document here because it represents one possible proportions of topics, right? And in the single topic model that I described, there can only be these vertices as possible configurations. So each document can be just one of these k topics, right? And this is unknown. But once I'm going to fix one of the topics, I'm going to draw multiple words here. And these are drawn from the same conditional probability table, which I represent by this matrix. Right? And the word is also can be represented as one of the vertices of another simplex with d vertices. Right? And these vertices correspond to different possible words in the vocabulary. Okay, and so in each document, I only fix to one of the possible topics, say for instance this one. And I'm going to draw different possible words, in the document. So I'm going to draw multiple words by fixing the same latent state. And that's why I'll call it a multi-view model, because I have multiple views of the same latent topic here. And that's what differentiates from the Gaussian mixture. Okay, so this is the generation process of the words. So let's now look at the set of how to think of the moments of this topic distribution. Right. So the first convention we'll use is that we'll represent the words through an one-hot encoding. So by that I mean that we use basis vectors to represent the words. So you have like a basis vector for each of the possible d words. And I'm going to represent using one of the basis vectors. Right? And what I have is this conditional probability table. Right? So if the topic was I, right, what is the probability the word takes a certain value is given by a probability vector. And I'll call that as AI. And because of this one-hot encoding where I represent this x as basis vectors, this is the same as expectation. The probability is the same as expectation. And that's why I can still write it as a linear model. I mean, this is the same linear model even for a Gaussian mixture. Right? Even for a Gaussian mixture, I know the conditional expectation of my sample given a certain component is the mean of that component. And even for discrete distributions, because I use this one-hot encoding, I can still write it as this conditional expectation. Right? So it's the exact same form here. But then I have now additional information because I have multiple different words generated in a document. So I have the same configuration of H, right? I have the same cluster in a single topic case, but now I have multiple samples being generated from the same cluster. And I have that information. I know that these different words belong to the same cluster. And that's what differentiates it from the Gaussian mixture. So let's put them side by side. I think now we can relate both of them. So in the Gaussian mixture, there are k different unknown means, right? So these columns A1 through AK represent these mean vectors. So in the topic model, these represent the probability of words under these k different topics, right? So A1 is the probability of the words if the first topic occurs in the document, and so on. Right? So this is the same generation process. In the Gaussian mixture, I'm going to select a cluster with I with probability Wi. Same here, I'm going to select a topic with this probability Wi. And this is where the processes change. So in the Gaussian mixture, I'm going to take the mean and I'm just going to add noise. And in the case we handled, it was a spherical noise. Right? But here, instead, what I'm going to do is, this is a discrete set of variables, right? So I'm going to use this conditional probability table, and I'm going to draw words according to this topic, right? But now I have multiple words drawn from the same distribution here. So that's what I mean by AI. If I fix this topic to be I have all these words that are drawn from the same topic. And that's what I mean by multiple views of the same hidden variable. So is that clear? I mean, if I were to write my sample here in the topic model as this AI plus the noise would be heteroscedastic, meaning it would depend on AI, right? Because in the end, you want a discrete variable to be generated. Whereas here we have this spherical Gaussian noise. So you see that there is a lot of commonalities between the two. The commonality is in terms of this linear model. So the conditional expectation of the sample given my hidden variable is just a linear form of the hidden variable, right? So it's this unknown matrix A times H. And using these multiple views of the topic model, it turns out that you can generate the same form of third order and second order moments as in the Gaussian mixture, right? And the Gaussian mixture, we reduce it to this form. In the topic model, again, you can obtain this form. Because the intuition is this M2 is now you take like, two words in the document, right? So what is the probability of co-occurrence of two words in the document? And we have these multiple views we can condition on this hidden topic and still obtain the same form. Because I know that there is this, with probability Wi, the topic I is generated in the document, and when it's topic I, the probability of obtaining different words is just AI times AI here. Right? And that's where the multi-view assumption is important to obtain this representation. Okay, so although you usually do not think of discrete and continuous distributions in the same light, when we think of the moments, right, and how they relate to these unknown parameters in Gaussian mixtures as well as topic models, you can reduce it to the same form here. And that's the strength of these methods, that you can see them in a unified light. So any questions here? So let's now, and this code snippet is available, on the website that I described. Let's just recap on how this tensor method works. Let's just take a very simple example, generate these samples and see how we can, what the method runs on, right? So we'll simulate the samples, whiten the samples as I described to obtain an orthogonal form, and then run this tensor decomposition method, the eigen decomposition. So this was the topic model with 3 words here. So these are the 3 views of my hidden variable. So how I'm going to generate is, first I'm going to generate for each sample the category, right, my hidden variable. And once I generate it, I'm going to generate all the 3 views, x1, x2, x3, by looking at this transition matrix or the conditional probability matrix C. Right, so very simple. I'm going to first, for each sample, draw this hidden category with some probability, according to some probability vector W, right? And then I'm going to draw these samples for x1, x2, and x3. These are the 3 views or 3 words in my document. Okay, so this is how I generate the samples. Now, I've generated the samples, I'm going to compute my second order moment. So the second order moment for the topic model is the co-occurrence of 2 words in the document. Right? So what is the probability that, say, apple and orange occurred in the same document? So here, well, I can take like say x1 and x2, right? These are the two views in the three-view model that I described. I'm going to take the second order moment here, right? I'm going to compute the empirical moment because that's what I do with samples. And then once I have this, I should find the whitening matrix, right? So the idea was that if I had my original, in the simple case, I just had two components. I had only two topics, and the probability vectors under those two topics were not orthogonal. But what the whitening does is it converts it to an orthogonal system, right? So how am I doing it? I'm going to first find the SVD, right, of the second order matrix, and I should just find the K SVD, meaning I just do the SVD of the top two components because K is 2 here. And once I do that, I'm going to use the eigenvectors and the eigenvalues with, according to this form here to obtain my whitening matrix. So once I have obtained the whitening matrix, what I'm going to do is whiten my data here. So each sample that I've obtained, I've done a linear transformation of this. Right? And now I'm going to use it to find, on this whitened data, I'm going to find the eigenvectors of my third order moment. So what is the idea here? So I'm going to find the third order moment with these whitened samples here. Right? So this was similar to like the multilinear transformation that I described earlier. There I had my third order moment, and then I applied this whitening matrix to each of the modes. But here I can directly think of whitening the samples and obtaining this empirical third order moment. Right? And we know that in expectation, it should be equal to a rank K decomposition, where the components of my decomposition are these whitened vectors. Right? They form an orthogonal system. And so we'll see tomorrow that this power method, in fact, has the interpretation of doing gradient ascent. But I won't, talk about the details here. But the idea is now, this was the multilinear operation that I described for finding the eigenvectors. Right? So I would do a power method where I would contract the tensor along two of the modes and hope to obtain the same vectors. So when it has converged, I know that I'm not going to change any further. And this I can do by directly computing the inner product with the samples. So this is again another implementation aspect that I will cover in the last talk in more detail. But the thing is, you never should form the tensor. I mean, at least in most instances, because the tensor is a d by d by d object, where d could be very high dimensional. Right? So we are finding now a three-dimensional array, so we don't have to explicitly compute it. But we are only implicitly doing these operations because in the end, like I only want to query this tensor, right, along these two of the modes and ask what the resulting vector is. So I can directly do this operation by looking at my empirical tensor and doing these inner products. And so this I can do as now the power method, right? And once I do the power method, I'm just going to deflate it, and I'm going to obtain the different components one by one. And you can see that in practice, this method converges very fast in very few iterations. I think this is just like 5 iterations, and it's almost very close to the true one. So this was the initial vector. If you initialize it here, it very quickly converges to the true. And this code is available online, so you can play with it. You can. It's very simple to even kind of build on top of it. But I wanted to convey the main ideas of 2 parts. One was to do this whitening. So using the second order moments, we can implicitly we would be orthogonalizing the unknown vectors in the decomposition, right? So how I'm going to do it is I'm going to take my samples and do this whitening transformation. And on these whitened samples, I want to have my third order moment. And to do the power iteration, I can directly do this multilinear operation on my whitened samples. So in each iteration, I'm only going to find this empirical estimate. Right, so I'm going to be updating this v in each iteration, right? and then I'm going to find what this resulting answer is. And when I'm no longer moving, right, that means I've converged, I'm or close to convergence. Then I stop, then I deflate, and then I find the next one, and so on. And that's what, and in practice, this works very fast. Okay, so today what we looked at was, two simple mixture models. One was the Gaussian mixture. The other was this topic models with a single topic in each document, which you could think of it as a multi-view model with 3 views, right? And this H was a categorical variable that selected one of the K topics, and then you would have at least 3 words being generated in each document by fixing the topic. And for both these models, we saw that you could reduce it to a bilinear and trilinear form in these unknown vectors. For the Gaussian mixture, they are the mean vectors, while for topic model, they are the probability vectors corresponding to different topics. And once we had that, we saw we could do tensor decomposition in 2 steps. One was this whitening, which converted the tensor to an orthogonal form, and the other was to do eigen decomposition on an orthogonal tensor, right? And then tomorrow I'll be covering the rest. Yeah.
When you're estimating the D-cube matrix using samples, is that sample complexity a concern?
It is, and I didn't talk about it today, right? So one is sample complexity, the other is also computation and storage, right? Because it's a D-cube object, so to compute it, you have to store it, then it's very expensive. Right, so we also don't want to. So here, what I
explicitly storing it, right? You just said that you won't be explicitly storing the matrix.
Exactly, I won't be explicitly storing. And the other thing is, I'm also like only looking at the Whiten tensor, right? So this is already a K-cube object here because the sample Y was the Whiten data. So I've reduced my D-dimensional samples to K-dimensional samples through my whitening. And on these Whiten samples, I'm going to do the power method. And so yes, the sample complexity is of concern, but I've made it more efficient by reducing dimension. So it's also, so this process of whitening and dimensionality reduction also helps in sample complexity. But it is an issue, and I'll try to talk about it more tomorrow. Yeah.
I think I have 2 questions. The first one is, how can you say this method actually can guarantee global optimum?
Yeah, and that is tomorrow.
Okay, and the second question is, I think it's a very nice framework, but I think it can provide the number of hidden states. Is that right? Because this kind of extension of PCA, so you can say from the eigenvalues how many number of clusters or how many number of hidden states you want to choose. Is that right?
So in practice, again, it depends on the model, right? So you could, for instance, look at the spectrum of the second order matrix, moments matrix, and decide what the number of components should be. So under some conditions, you could use that as a way to consistently estimate the number of components. You could do cross-validation, you could do different ways to choose K. This is anyway true for all the methods with hidden variables, right? You have to choose a model order, and the same would be applying here. Any more? All right, so we'll meet again tomorrow. Thank you.
That's right. Make sure that.
And that's not the other also. I'm computationally efficient. Yeah, so not for these models, it would be done, right? Maybe for other models. So we had feature model. I mean, as I said, like the issue of like computing with samples, right? So the higher order moment you go, like the more perturbation. Yeah. Yeah. So pairwise is not enough. That's why. Can maybe like because it's a bit more detailed, can we mention the others and then? Oh yeah, we had an email of the conversation. Hi. Oh, okay, great. Yeah. Yeah, I mean, there was a lot of material covered, but I hope that it was, but then the slides are also available. Something is not clear. Any questions you have? So I think I have like, yeah, more. Let me see. If someone has a short question, we can first finish that. Or everybody has long questions. Okay.
I'm just confused. By the way.
I know there.
No, don't worry.
I know there's another talk. Which for a minute I forgot. I was not able to hear done.
Okay, 3 minutes. Oh, good.
You told me, yeah, but thanks, Alex.
I'm really sorry that I got you late.
No.
It's not bad, but it's just annoying for you. Well, it's almost done. Yeah, it's up to fix up something. I'm not sure. Maybe. It's okay. We just have PJ. Yes. I have PJ. Yeah.
No, yeah, you can go
Okay. So if you need a regional space, it's 8,000. And we can show you. Yeah. But
Our three space around.
Yingda, can you hear me? Great. Okay, so maybe we can we start the camera again, please? Okay, apparently let me quickly start the camera and then announce. Yeah, just if you can stand, yeah, just stay where you are. Just need to make sure you're nicely in focus. And for that, you basically invoke an edge detector. Okay. Okay, so welcome everybody to the second week's track of somewhat more applied practical sessions. And it's my great pleasure to have Marcus Weiler here. He is at Microsoft, principal research scientist there well, the abbreviation is CISL, and I think I'm going to butcher it somewhat, Cloud Information Services Lab. Okay, good. So, in any case, he's going to talk about REEF, and basically that's a alternative way of performing big data analysis, and he's going to tell you all about that during the week. Okay, Marcus, take it away.
Thank you. Thanks for coming. I want to start with, first of all, thanking you for showing up and for Alex and Sigurd and the organizers to invite me, but also to the REEF team back at Microsoft, two of which are here. Sergey and Yingda have been here last week as an attendee. They will help me out during the lecture, and I will ask them to identify themselves once we actually meet them. Shravan, who's probably watching, still hard at work coding the stuff up that you will look at on Wednesday. So great thanks to him. This tutorial will be hands-on keyword beginning on Tuesday. So on Tuesday, please bring a laptop, bring a charger, because we will compile code, and even though Intel claims otherwise, Haswell doesn't help with compiling code on battery. The whole tutorial will be super pedestrian in terms of the kind of machine learning we will do. The most advanced algorithm you will see is batch gradient descent with line search. It will be fairly advanced on the system side. So this is kind of the exact mirror image of all the other tutorials that happen here in the morning and before this. And that's why I ask you to ask questions early and ask them often. Because I don't really know what your background is, and it's really tricky for me to judge that by just looking at you while you're rightfully staring at your laptop. So please ask questions early and ask them often. Okay, so I entitled this Towards Resource-Aware Distributed Machine Learning. Towards on paper titles and tutorial titles always means that we don't quite know yet how to do this. Right? That's just the honest answer. And one of the more selfish goals of me being here this week is maybe some of you can help us figure it out for real. Right? So I will mostly talk about open problems towards the end of the session, and maybe one or two of you will find those interesting enough to actually start working on them. But before asking that question, we have another question, that is, why should I even care about distributed machine learning? Right? Machines are getting bigger, you can stick 4 GPUs into a single machine, you can get 512 gigabytes of memory into a single machine, so why care? Well, as probably every single speaker of the last week has told you, that sometimes you have to, because you end up with larger than RAM data sets, and the economics of the problem we are solving is of the kind where using many machines is very feasible from an economic perspective. If you train the advertising system for Yahoo, it doesn't matter how many machines you burn in the process, because every little tick in precision uptake will give you some money in return. And of course, streaming the data from disk will help you to some extent doing that. And one fairly successful example of that is John Langford's Vocal Rabbit, that streams the data from disk over and over again in a very efficient way, and therefore can allow you to learn from larger than RAM data sets. Also, efficient data structures will help. So for example, if you take the now tiny Netflix data set, and most people represented each individual entry there as a double, which is 8 bytes. But it's only a number between 1 and 5 stars, so why waste 8 bytes on that? So you can get away with a single byte. Tricks like that help you, but ultimately you might hit a data set that's too big, and where the performance from disk is not good enough, so you want to go to multiple machines. The other problem, obviously, is if your model is larger than RAM, then streaming from disk is really impractical, because often you have random access to the elements of your model. Think of a matrix factorization problem where you need to update individual entries. So streaming from disk is no longer an option. If you hit models that are bigger than memory, you have to go onto multiple machines. And of course, if you happen to have a computation that is very expensive and you need all the CPU power you can get, then you also will find yourself in a situation where going onto multiple machines is beneficial. So if you think about, Quark was here last week and talked about deep learning. Their paper at NIPS about the DeepNet image classifier used 1,000 machines to learn 1 billion parameters. 1 billion sounds huge, but think of it in data size. if each of those is a float, you end up with 4 gigabytes of memory used. Yet they used 1,000 computers to do it. Why? Right? The reason is more CPUs help in this case because the problem is fundamentally CPU and not I/O bound. Okay, but what about all these many more smaller data sets out there in the world? The vast majority of data sets easily are in the range of 0 to ½ terabyte, so you can load them into main memory. The vast array of models that is out there is way smaller than ½ terabyte, so you should be able to do things in main memory. Why should you care about distributed learning in those settings? Well, first of all, it might be all the computer you have, right? When you join any of the internet companies, what you will find is there are clusters of commodity machines. And commodity by now also means like triple-digit gigabytes of memory, but still, you have these clusters that are designed to be multi-use such that they are affordable, right? So you have other frameworks that also need to run there beyond machine learning, let's say billing, and you want to make these clusters as multi-use as they can be. The other aspect that comes into play, especially if you talk about systems like MapReduce and Scope and now Hive, that all produce data, they produce the data already pre-partitioned. And I'm going to go over the details of what that means. So your data is fundamentally already distributed. So in order to run it on a single machine, you have to reunite it on that single machine first. Lastly, the machines in those clusters, they are not purpose-built for machine learning. Right? As much as we like the machine with ½ terabyte of memory and 4 GPUs, that's not what you will find in 1,000 copies in a data set. What you will find is some sort of a trade-off between all the different users of those machines and what is the cost-effective configuration of those machines. So for example, GPUs and CPUs are not chosen by peak performance, but by performance per watt. Because at the end of the day, you have to put electricity into those computers, and you have to cool that electricity away again. So using machines that can give you more performance per watt that they consume is hugely beneficial. And also the other workloads that you typically find on those clusters, they are not CPU bound. They are most often I/O bound. Read a terabyte of data, find that one nugget of information, spit out a megabyte of output. That's a very common query case, right? So for that, you don't need much CPU. You need lots and lots of I/O capacity. Just as a point of reference, Yahoo published, or Facebook published their cluster configurations, and they have 12 disks per CPU. So it's all about I/O performance for those. So the CPU-heavy machine learning that we would like to do is often met with machines that are not quite the ones. And going on to multiple machines is of real help here. Okay, so I want to start the kind of main part of the tutorial with going over a very brief history of some recent open source distributed systems for big data processing and what people did to make it better and kind of where we are today. So, who has used Hadoop in the audience? Just about anyone. Who liked the experience for machine learning? You will like my next slide. Okay, just for those who didn't raise their hand, Hadoop in version 1 came in with 2 components. HDFS is a distributed file system that has some centralized name node, which you can think of as a database that keeps track of where which file is. The files themselves are chunked into blocks. So if you have a gigabyte of file, that typically ends up being 4 blocks, each 256 megabytes in size. And then in Hadoop 1, each of those blocks would be stored 3 times on different machines. So if you lost a machine, you still had 2 to pick them up from. If you had a disk error on one of the machines, you still could follow a majority. MapReduce then was the way in which you could write applications for that cluster. In MapReduce, what you give to the cluster for execution is something very simple. You specify some input folder or files in HDFS. You specify a map function that is applied to each of the records in the data set. And it spits out key value pairs, let's say a word and whether or not it was found in spam, whether or not it was found in a document that was representing spam and emails. And then you have a reduce function which gets for every key, in this case the word, all the values, in this case the count in how many documents it was, and reduces this. And just assume you sum them up. If you do all of this and then write it to disk, you have built yourself a naive-based classifier for spam, right? Because you just count words. Now this is super nice if you have algorithms of this kind, right? Because MapReduce does all the heavy lifting for you. It figures out on which machines to run. It figures out when an individual mapper fails, just to rerun that part of the computation. It solves all this sorting out the data in between map and reduce. So the mappers put out key value pairs. They need to be shuffled or sorted to go to the right reducers. All of that is being taken care of, and it's super nice. At that level, it is super nice. So a lot of people came up with the idea of doing distributed learning on MapReduce, or more specifically Hadoop. This is generally a good idea because MapReduce as a logical programming model fits what's known as the statistical query model really well. And in the statistical query model, you express your algorithm as queries against your data set, which produce you statistics of that data set. Think of gradient descent as another example in naive-based. You compute the gradient on every data point, and you want to have an aggregate statistics of that. So the map function would compute gradients, the reduce function would sum them up, and a counter, and then as the output, as the very last step, you divide by the counter to get the average gradient. So this sort of thing is very natural on MapReduce. That's why there's a ton of papers. There have been whole systems built around this idea. The open source one would be Mahout, who built machine learning algorithms around that insight. What they've all, without failure, have eventually discovered is that it's not such a great idea on Hadoop version 1. Because Hadoop MapReduce did not support, or still does not support, but there are better options now, does not support iterations. So each time you submit one of these MapReduce jobs, it is exactly load some data, apply the map function, shuffle the data around, run the reduce function, store it on disk. Now, if you have an algorithm that needs 100 iterations to converge, you load the data 100 times from disk, you apply the map function 100 times, you have to do that anyhow, then the mappers write their output data to disk, where it is shuffled, and the reducers eventually do the same. So you have a lot of disk involvement that is the same in each and every of the iterations. Even worse, you have the scheduling overhead. If you have a large cluster, a couple of thousand computers with tens of thousands of CPUs, and you walk up to one of them and you say, here's my job, please run it. The one poor machine in Hadoop 1 that would have to figure out where to run your job would become the bottleneck, and you would sit there for like 10, 20, 30 seconds before your MapReduce job starts. Now think about an algorithm with 100 iterations and half a minute lag before anything starts and a minute of overhead in each iteration. That quickly becomes infeasible in practice. Now there's of course the completely opposite problem where MapReduce is a bad model for computation. And that's for all these graph-based algorithms where you have to send very small amounts of data in between different nodes in your graph computation. That's where MapReduce is just not the right logical model. But even where it is the right logical model, you run into all these issues of overheads. So what have the bright people at Yahoo and otherwise done at the time to help themselves? Well, we built map-only jobs. What we did is we wrote a map job that didn't have a reduce phase, and we blatantly lied to the underlying system. Instead of actually computing a map function on a record, we used that first map call to hijack the machine and run our own computation. So the first map call would give us some control over a process on the machine. And we instantiate a learning algorithm with, for example, MPI as the communication primitive, and then run in the map machines and eventually releasing the mappers when we are done. So I like to call that Hadoop abuse. We organized a workshop back at Yahoo about this where we said, let's bring the Hadoop team and the Hadoop abusers into a room, segregated by a nice line in the middle, and have us talk about this, right? Because this solution is clearly not good to lie to the system. At the same time, it's the only thing we could do given the clusters that we have. I want to first talk a little bit about the kinds of abuse that people did, And then I want to talk about where the industry as a whole is moving to avoid this sort of situation. So let's talk about one kind of Hadoop abuse that was super prevalent and is kind of in decline now because better opportunities are out there. Think about the situation where these P's are your data partitions, and then you have some additional computational nodes that you obtain. Then you send some statistics up that tree and provide new model updates down. Gradient descent would be a good example for an algorithm that you can implement in this way. There's a couple of abuse papers out there. The first of which is the decision trees on Hadoop paper by Jerry Yee. He actually tried implementing it in MapReduce, and in the paper makes a really nice case why that is a bad idea, and then runs an open MPI job as a map-only job on Hadoop instead and obtains great performance gains in this. The other very popular solution in this space is VW from John Langford and al. What they do is they realize that this is the only computational operation that they need in terms of a communications pattern. Aggregate some data, redistribute it to everyone. This is an MPI known as allReduce, and they made a version of this primitive for Hadoop. So what they do is they set up a custom server on the cluster that helps them set up the computation where every of the mappers checks in. Because that's a crucial problem, right? You have your mapper running, but Hadoop didn't tell you on which machine it was running. So the first thing that your map task will have to do is check in with some known location and say, hey, I'm here and I'm ready to compute. So they have their own server for this, where Jerry Yee still used HDFS for the same purpose. And then Wopel Wabbit goes ahead, builds a binary aggregation tree, and commences the execution. They did a really interesting additional trick, and that is, we'll come back to that at a later time, but some of the machines are always slow. For those of you who have run Hadoop MapReduce jobs, that's the curse of the last reducer. You sit there and you wait for the last reducer to finish. If only that thing was done, your day-long job would finally be done. It's very well known that some machines, they go bad and then they are slow instead of broken, and you just sit there and wait. In order to avoid this in an iterative computation, what they did in VW is they run the first iteration on more than the necessary machines, using Hadoop's speculative execution, which is designed to conquer this and run some mappers on more than one machine. And then they just used the first one that completed the first iteration, following the insight that if it is fast in the first iteration, it will stay fast. Turns out that that is actually true, and it works really well. Lastly, I also contributed to this kind of abuse. We took this kind of to new heights by declaring a new programming model on top of it. We said, okay, what we really want to do is we have some workers that compute on data, then we aggregate data into one place where we perform an update. Think about the workers computing gradients, the aggregate summing things up, and the update function performing a decision as to how far the step size shall be and all that. In this case, the good news about that approach that we took is we didn't abuse the file system for synchronization anymore. We had kind of better ways with Zookeeper. Okay, the other kind of abuse that people have built on top of Hadoop to kind of avoid the inherent trickiness of writing things in MapReduce that are fast is if you take the graph view where your data and your model are partitioned, for example, all these cases where the model is really big, and then you want to do message passing in between these graphs. Given that this is at CMU, a very good example of that would be GraphLine. Right? On top of Hadoop as map-only jobs, I'm aware of two systems that do this. Number one is Apache Giraffe. Started at Yahoo, is now at, most of the developers are at Facebook. They built a graph processing framework on top of Hadoop MapReduce, where each of the nodes gets some input in each iteration, computes new output, and in between the iterations that get shuffled to other nodes in the graph. But crucially, for the purpose of this argument is, they still did this by building map-only jobs. The other example is the Yahoo LDA implementation that Alex has worked on, and Shravan, the co-worker of mine who worked on the summer school with me. They also instantiate a graphical model as a map-only job, use HDFS for synchronization, and do all the things that are necessary to make this sort of thing go fast on Hadoop, which in essence meant lie to the scheduler wherever you can. Okay, so why am I telling you this? Because there are problems with this approach. And the problems come in two flavors. One problem is problems for the abusers, right? The other one is problems for the cluster. Let's talk about the abuser first. First of all, there is a fault tolerance mismatch here. If you are running in a Hadoop cluster and one of your mappers fails, the same thing for a MapReduce is to take the work that that machine was supposed to do and put it onto another machine. Now, you don't actually have a mapper anymore. You don't know whether this sort of operation is safe for what's actually going on in those mappers. And just about any of the frameworks that I mentioned, with the exception of Giraffe, don't deal with failure because of it. Not because Hadoop wouldn't detect it or anything, but because it's so awkward to deal with the policy that is in Hadoop that would solve it for you when you're not actually writing a MapReduce job. The other problem that arises is that there's a resource model mismatch. In MapReduce, you would assume that it's a good idea to execute the mapper on a machine that holds the input data. So instead of taking the 256 megabytes of this block that you want to compute on and shuffling that through the network to a machine that runs your map code, you instead take the 20 kilobytes of your map function, send that to the machine that has the data, and compute it there. That makes perfect sense for MapReduce. It makes absolutely no sense whatsoever if what you're doing is load that data into main memory and then communicate a lot with all the other machines. Because for that scenario, you would want to be close to each other in a network sense. So in traditional data centers, that would mean being on the same rack with all of your mappers. That's not a consideration that makes any sense for MapReduce, but makes every sense for these iterative computations. So you're in this awkward mismatch situation again. And lastly, it's a lot of work to write any of these systems, because in addition to having to solve the systems problem, which includes building up networking, figuring out cluster membership, whether or not machines are still there, doing all the data transfers that are necessary, you also have to figure out creative ways of lying to the scheduler. So your problem didn't get easier, but harder. On the other side of this, there are a lot of problems for the cluster. And the biggest one of those is those kinds of abuse scenarios of Hadoop violate the MapReduce assumptions. So for example, if you have a map function, you could assume some sort of proportionality between input and output. If it reads 100 gigabytes, it will produce 10 gigabytes. Okay, if I send it 200 gigabytes, it will produce 20 gigabytes. So I can use that as the scheduler to make optimization decisions. Different from that, these MapReduce jobs that aren't actually MapReduce jobs, they load nothing, then compute really, really long, and then produce some output. And while they are computing, they are hitting local resources, like the local disk. So if you have these bursts of local disk use, and you don't know what's going on, it's a reasonable choice by the cluster management system to say, this hard disk must be broken. Because from the perspective of other jobs, it's sometimes slow. Because the cluster has no clue that what you're actually doing is using a different computational framework. The other situation that arises is if you are in a shared cluster. This kind of abuse is very disrespectful to other users. Because you're violating all sorts of scheduling assumptions of the underlying system, you might make someone else's last reducer slow by doing so. Right? So in exchange for your job being done quickly, someone else sits there and bites their nails and wonders, oh my gosh, I have a paper deadline, it's not done yet. Right? So this is not a good situation to be in. At this point, I want to kind of do a little side note of how I like to think about clusters and clouds. So if you have a cluster, like the kind that you would find in a typical research department, there is almost exclusive ownership. Right? A research group has bought it, they get to use it, they have some kind of armchair or whiteboard scheduling as to when who gets to use all of the cluster, because in order to write the paper, you have to run on all of the nodes at once to get that nice scale figure at the end of the paper. So there's some exclusive use. In that sense, idle time is bad, because you already heckled your coworkers into getting the cluster for this week, and every single minute that not all of the CPUs are doing work is a bad situation for you, because you already, quote unquote, paid for it. The cluster is also unelastic. You have these 100 machines, and unless you write a new grant proposal and get some more machines, it's not going to get bigger anytime soon, or smaller, or anything like that. Smaller maybe if things fail and you don't have budget to replace them. So the optimization goal then for your work is the wall clock time to a solution. If you build a distributed learning algorithm, the only optimization criterion you care about is how fast does it run? Does it run on more CPUs faster than on less? And even if one more CPU brings me a millisecond of speed improvement, I will do it because I already paid for that CPU. Right? There's no other incentive in this game than to use the machines as much as you can for as long as you can till you're kicked off and get as many jobs through in that time. The cloud, on the other hand, is rented on a per resource basis. Think of the most basic cloud. When you go up there and you rent virtual machines, you pay for them either in hour increments on some clouds or in minute increments. But at the end of the day, you pay for it. You pay for it by usage. So there is a very strong incentive to actually have idle times as long as you switch off your resource usage during that time. Because you don't pay for it when you're not using it, different from the cluster that you have in your basement. And you can write elastic applications. You can decide at runtime of your application to just add some more CPUs or to remove some or stuff like that. So there's a real chance. So the optimization goals become much more interesting. I won't have time to talk about the implications of that for machine learning, but if you think about it, you could think of the cheapest way to compute a model given a deadline. This is a very common scenario. Sunday morning, 5 a.m., you need the new advertisement model, and you have the input data at 2 a.m. What do? Do you rush on 1,000 computers to have it done by 2:15, or do you kind of do a leisurely pace where you might incur less cost? Another problem, optimization goal could be you want the fastest path that you can get within a given budget. It's kind of a variant of the cluster situation. Okay, for both the cloud and for this problem of MapReduce app use, the industry is converging on what's known as resource managers. So resource managers, there's a couple of them coming up in the literature in the last 2 or 3 years. The first of which was Apache Mesos coming out of Berkeley. Then Google wrote a paper on theirs, on Omega. And then there's Apache Yarn, which is the resource manager that's part of Hadoop 2. So whenever you get to a Hadoop 2 cluster, you can assume that MapReduce is not your only option. What your other option is, I'm going to talk about for the rest of the tutorial. So these resource managers vary greatly in how you get resources, but they don't vary in what it is that they actually manage, right? Because I said resource managers, but what is a resource and how is it managed? So they generally view the whole cluster as a collection of containers. They can have varying sizes. I'm just going to use this kind of grid visualization for the rest of this tutorial, where each of those containers is a slice of a computer. Think of it as some amount of memory, some amount of CPU, some amount of networking, some amount of disk. It's a reservation for resource utilization on an individual computer. So why is this cool? You can now walk up to this resource manager and say, give me 5 5-gigabyte containers with 2 CPUs each. And someone else walks up, no, my resource utilization is of the form, I want 1 container with 64 gigabytes of memory and 2 CPUs or 5 CPUs. So we now can enable what's known as multi-tenancy or even true multi-tenancy. On the same cluster, you can run many, many different workloads and negotiate in between them. For example, you could have a streaming job sitting there that needs to satisfy some latency constraints that you have, right? You have a click on a website, and that needs to be represented in the front page advertisement module within 2 minutes. So that guy has certain resource requirements. Another one might be a batch job that needs to be done within the next 5 hours, but who cares when within this window? Right? Yet another one might be an interactive session where someone would be really upset if it all of a sudden would go slow. But also what this enables is, or shall enable, I should say, is that you have many, many different users of the same hardware sharing it under some sort of resource governance. By all of them having to go through the resource manager to get them, you get billing, and you get separation between the users. But it's tricky to write applications in this world. I'm going to try to visualize that in a couple of slides. So think about about a job that sits there in these blue containers. Do they actually come across? Yes, they do. You have your job sitting there in 5 containers, and it's running, and it's doing some, let's say, MPI-based message passing algorithm for a graphical model. Now disaster strikes. Some of the machines disappear, right? So you need to deal with that somehow, right? One perfectly fine way is to crash and restart. That's what a lot of people argue for if their system is fast enough. Then there might be another situation where someone else is more important on this cluster at that time and takes away machines from you. This might look to you just like a crash because the machine is taken away from you. But another situation might be that you get told up front that this will happen in, let's say, half a minute, so you better vacate those machines. That's the difference between hard and soft preemption. Hard preemption is your machine goes away. Soft preemption is you get told to please vacate some machines. If you fail to do so, soft preemption turns into hard preemption and looks like a failure to you. Lastly, you might be the lucky job, right? So some resources just became available, and the resource manager makes it known to you that if you wanted 10 instead of 5 containers, you can have them. Now, how do you make the decision whether that's a worthwhile endeavor? Right? You might be at the end of your optimization anyhow, and reshuffling the data onto 10 machines might take longer than what you would gain. So it's not obvious what to do in these situations. And I illustrated it with a couple of examples, kind of the classical examples. If you write a MapReduce engine, think about yourself as the person who implements MapReduce. They have to consider the situation where failure occurs. And the very traditional way they do it is they just write things to disk. Right? That's why MapReduce is so disk intensive. Everything that has been computed gets written to disk, such that if the computer that computed it goes away, it doesn't matter. The other situation that you typically have in MapReduce is you only know how much data you have for the reducers when the mappers have run. So at that very moment, you need to decide how many reducers you want to schedule, and you might find yourself with wrong assumptions from initial. You might find yourself in a situation where you initially made the wrong assumption. So you need to scale up, right? In those cases, it's kind of known, right? The database literature has been at this for 30 years. They have their answers. In machine learning, we don't. Another example that people care about on these clusters is, of course, machine learning, which, as I was mentioning, MapReduce is a really poor model for iterative computation. So what we want is more like MPI on these clusters, right? So we want to run an iterative computation on this cluster, and we want this to be supported by the underlying infrastructure. And of course, I also already mentioned that you want to do graph processing on these clusters, right? So you have your shared infrastructure, you want to instantiate a graph processing system under all of these stresses that come onto it, right? Machines fail, there's soft and hard preemption, there's the opportunity to scale up. How do you make decisions in this world? So we are, of course, not the first people to talk about this, right, in the Reef project. Lots of people have built engines on top of resource managers in the last 2 years for just about any of those use cases. There are graph processing frameworks, there are iterative MapReduce frameworks, there are SQL engines, what have you. So this is good, because now those people all get to share one cluster, right? You no longer have to have that one MapReduce cluster and then lie to it if you want to do something else. You now have a principled way of running on this. But I would argue that it is not quite there yet, because what we now have is silos on the cluster as opposed to on different clusters. Each of those silos is again hard to build, right? We have done very little to make the life of the person implementing the graph processing system easier. We have also done very little to make machine learning easier on those clusters outside of not having to lie to the system anymore. And in practice, those silos form pipelines. So if you think about last week's tutorial with the parameter server, the data that you run the algorithm on needs to be processed by something. It needs to be generated by something. And if it's not a well-known data set that you go to a website and download, you're probably the one who does that. And if it's fresh data every day, you better have that working in kind of a repeatable fashion such that you can train new models on a predictable schedule. So in practice, what you will find is there is some sort of SQL or MapReduce-like processing going on that feeds into your machine learning algorithm. Now, if you have these different silos, this is really inconvenient, because each of them has different failure scenarios, each of them has a different configuration mechanism, each of them will have to schedule containers on their own decision boundary and all that. It's really tricky. So this is where Reef comes in, where we try to build the next layer on a resource manager that is still broadly applicable to all the different use cases. And the way that I found successful in thinking about Reef is, if the resource manager and the distributed file system form something like a cluster or cloud operating system, then you can think of Reef as the standard library. Just like on your laptop, you have applications ranging from database servers over compilers to Photoshop. They all need a memory allocator. They all need to open files. They all need to connect to the network. At least I hope so. So what we try to do with Reef, we try to be broad in appeal. That means that we favor mechanisms over policies. What do I mean by mechanism and policy? A mechanism in fault tolerance, for example, would detect the failure and provide options. If a machine fails, Reef will detect that and tell your application, but then it's up to your application what you want to do with that knowledge. Do you, for example, want to crash because you can't tolerate failure? Or do you, for example, want to figure out what ran on this machine and send it to another one? Right? MapReduce, on the other hand, couples a mechanism with a policy. The mechanism there is the same. It detects that the machine failed. But there's also a policy, and the policy is run on another machine again. What if you don't want that? Then you have to lie again, and we are in all that business. The other goal that we have with Reef is to avoid silos. We will touch that a very little bit during this tutorial. But the core insight is that we recognize the need for these different frameworks. Right? You have lots. The systems literature is full of papers that suggest the one system to rule them all. If only everything was written in MapReduce, then we wouldn't have this problem, right? If only everything was written in SQL, then we wouldn't have this problem, and Oracle would solve it for us, right? In reality, that doesn't seem to stick, that sort of notion. Because new applications come up in machine learning, new ways to compute things come up. So it's not going to stick anytime soon. So what we try to do is, what is the kind of highest layer we can build that is broadly applicable and still allows this handover? So a question that we ask ourselves is, if the data comes from MapReduce and the computation happens in MPI, how can we make that efficient? Right? Lastly, for those of you who have used MapReduce and Hadoop, it's incredibly painful and comes with a high performance hit if you do anything but Java development. Because it's just not meant to be anything but Java. So we did some work in Reef to make that a little easier. It will be not applicable to this tutorial where we do everything in Java. But if you have C code that you want to kind of distribute on a Hadoop cluster, Reef can help. Okay, so I told you a little bit about why we did Reef, what it tries to accomplish, and all that. Now I want to tell you about how a typical Reef application actually lays out in time. So as I was mentioning, we assume that there is some sort of resource manager in this cluster. As it's called yarn, it's this big ball of yarn in the upper right corner. And we assume yarn to deal with all the resource governance. So when you submit a job and you actually don't have a user account there, that's yarn's problem, not ours, right? To tell you that you need to go to another cluster. Then per job, so per application or per algorithm or whatever you want to run on the cluster, we have the notion of a job driver. That's the master of your computation. It deals with all sorts of control flow decisions. For example, what to do when it starts up, what to do when a task fails on a machine, all that sort of thing. It also needs to figure out when it's done, right? At some point you need to exit your program. In this case, the driver goes ahead and asks for 3 containers that are on those machines which already have some data, and 3 more. And because this is a good day on the cluster, we immediately get exactly what we asked for. This might not be the case when you run on an actual yarn cluster, because those resources might not be available for you at that time. So what we then instantiate in those containers that we get back from the resource manager is evaluators. An evaluator is a process that sits there idly waiting for commands. That's how you can think about it. The evaluators crucially outlive anything that you ask them to do. So if you send a task to them, in this case, 2 different tasks on 6 machines total, and they can then execute in the evaluator. Now, of course, as I was mentioning earlier, disaster strikes once in a while, and a machine disappears, or a container disappears, typically in the form of a whole machine disappearing. In that case, we fire an event to your driver, and the driver then has options on what to do. Right? It has to figure out, hey, I lost a machine. Do I do anything about it? And if so, what? In this case, the driver wants to reinstantiate its computation, goes to the resource manager, asks for a new evaluator. Luckily, it gets it, and instantiates the computation in that. Right? Again, the decision what to do in this case was the application's decision. Reef didn't make that call. Reef made it easy and very obvious that you have to make that call, but it didn't decide. Now, of course, tasks are done at some point, in which case the evaluators stick around. This will be very crucial later in the talk, where you can think of the first task is the one that loads data into main memory, and then it is in the main memory of the evaluator, and then the second task actually computes with it. That helps with this whole handover between different frameworks. You can think of MapReduce loading your data into main memory, and then you send your MPI program to those computers. Okay, in this case, we just send something else there. Okay, so why is this retaining of evaluators cool? So there are a couple of use cases where we think it's useful, and we have yet to find some more. If you have a MapReduce job, so often when you do machine learning, you want your data partitioned in some convenient sizes. Let's say your maximum container size is 16 gigabytes. Then you want to have your terabyte data set split into 16 gigabyte blocks. Right? It's very convenient to do in MapReduce. You just assign to each record that you read a number between 0 and 15. You're done. Right? And you set the number of reducers to 16. Now you have files. Now you have to schedule yet another job that loads it and runs with it. What you can do with Reef is you can run the MapReduce job and then just change out the task on the reducers from the task that used to do the reduce to a task that computes with it, with your algorithm. Now, and then, of course, we can set up some sort of iterative computation because the machines outlive any particular task. Right? You can send a task, wait for its completion, decide what to do next, and send the next task again if you have a purely iterative computation. Lastly, it's useful, we haven't built anything that uses that yet, for interactive queries, where you load some data into main memory on a couple of machines, and then you just keep submitting code to that data from an interactive prompt. For those of you who are familiar with Spark, that's pretty much how that would look like. Okay, so I walked you through a control flow in Reef, and don't worry, we will do this much slower and with gory details in code again. But what I want you to take away from this is, it seems like a lot of work compared to writing a MapReduce job, but it's actually much easier than not having Reef. Because what Reef does for you, it centralizes all the control flow decisions. So, for example, if an evaluator crashes at the other end of your cluster, Reef's default behavior is to crash your job. That sounds like not much. But why on earth should your driver crash just because something else in another virtual machine threw an exception? Right? That's a feature, not a bug. It's really hard to accept, but that's the case. We also centralize all the error handling. When anything in an evaluator throws an exception, division by 0, out of memory, anything of that kind, and the code, the task that you submitted to that evaluator doesn't catch it, we will catch it, send that exception to the driver, and present it there. The most useful case for that is the out-of-memory situation. When a task runs out of memory, that's typically because you didn't ask for a large enough container for it. So in this case, the task can do nothing about it, right? It's the container that it has. But the driver can go ahead and ask for another container that's bigger and reinstantiate the computation there. This design is also fairly scalable because in the driver, everything is event-based. This goes down to the point of there is no entry method. You get an event that your driver can now start, and that's when your application starts. This allows us to schedule these events on as many threads and CPUs as we find in that machine where your driver happens to run. So this is fairly scalable as long as you don't write blocking event handlers. And it should scale easily to thousands of containers. Also, the Reef design is mostly stateless. So the driver itself keeps almost no data. That is important if you consider the case that the driver itself fails. So just like any other evaluator or container, the machine that the driver runs on can fail. And then you need to restart. And if the driver has gigabytes and gigabytes of state that it needs to continuously maintain on disk such that this restart can happen, that would be a bad situation. So Reef is in itself as stateless as we could make it. Then of course, if your application has gigabytes and gigabytes of state in the driver, then, well, we can't do much about that. You'll hear me talk also about two support libraries in Reef that we built for Reef. Wake is that layer that makes this event-based programming possible for us, and that sends the events across the network and all that. We will only touch that very, very thinly by implementing a couple of interfaces, but it's not something that you need to consider yourself with during this tutorial. The other thing that we built, and that's actually fairly crucial for the tutorial, is Tang. And I want to today give you kind of the feature, what it does, and then later in the week, how it's used and how it does what it does. So, for those of you who have written distributed systems or have used Hadoop, how many of you have run a job purely to see whether you misspelled a parameter? A few. The other ones are too modest to say yes to this question. Yeah, because configuring distributed systems is incredibly hard. The driver makes some decision about how the configuration should be for a task executing somewhere else. It sets paths, it sets memory sizes, it sets all of this, right? And then the Hadoop team has the great idea of renaming the memory size of a mapper, right? The parameter for this. You misspell it, it goes unnoticed till you run out of memory. Right? So this is bad, and it's hard. So what we said is, okay, let's do something about it. Even though it's not, as machine learning people and systems people, not on the first on the list that you want to write a paper about configuration systems. But hey, let's do something about it. We should get into a better state. So we view configuration as dependency injection, which enables early and static checks of your configuration. So I want to show this in kind of a feature form today, and probably tomorrow we'll get to how it's actually used in practice. So what you might find on a Hadoop cluster, when you say, let's say you have a map task that spawns another process that shall execute ls in this case. A very common exception that you might find is some sort of null pointer exception, because you accessed an entry in the configuration that wasn't actually there. Default behavior is to return you a null. Then you pass that on to another method in your program, which will throw the null pointer exception. And now you sit there trying to figure out what on earth went wrong, and why did I have to sit here for a minute to get that error message out of my task? Right? So what if you could instead get this? Some system tells you there's an unknown parameter called command that no one asked for, but it's in the configuration nonetheless. There's a required parameter called CMD that isn't set. It's the typical rename situation, right? Tang makes this sort of exception, this sort of error message possible. And in many, many cases, we are there in terms of being this close. Okay, so now we fix this. Now we have a task that depends on this information, but we bind that task to another parameter that expects an evaluator, right? So this is a typical type error in your configuration, and that would just tell you, hey, you gave me the wrong kind. In this case, we fix it the other way around by actually asking for a task. And then if you think this through till the very end, you get kind of a dependency graph of objects. In order to instantiate an evaluator, you need to know which instance. Well, the yarn evaluator. The yarn evaluator in itself depends on a task. Which instance? Well, the shell task. The shell task has a parameter called CMD, which needs to be bound, in this case to ls. If anything in this dependency graph is not correct, we can tell you at the very early times. If you misspelled in the compiler, if you miss required parameters, then we have static analysis for that. If you submit a task to an evaluator that doesn't actually have an object that you require, we tell you before you submit the task, tells you already on the driver. So this saves hours and hours of debug time. I cannot overstate how much this sort of thing helps. And for those of you who have tried to write distributed applications, this is very obvious. For those of you who haven't, you just sit there saying, what is he talking about? It's easy, right? You set a key value store. I'll get back to that easy part. Okay, this was all about control plane, and this is kind of utterly boring because at the end of the day, we want to do something with data, right? We have some data on this, we want to do some computation on it. So in Reef, we are working on a couple of data primitives. One of them is fault-tolerant communication. If you have two tasks talking to each other, and you must assume that one of them might disappear at some point, then you have some ways of dealing with this. Number one is you have some sort of name service that keeps track of where is which task went, assuming that it will be reinstantiated. The other one is you have a mailbox. You don't have direct communication in between tasks, but one task sends to the mailbox of the other, and when the other eventually comes online, it fetches it. Then something that we will do a lot of work with during this tutorial is group communication. And by that we mean what the MPI standard calls collective communications. So for those of you who have written MPI programs, that's stuff like broadcast, reduce, or reduce, scatter, gather, and all that. But none of the MPI primitives apply directly to this world, because the MPI standard is very strict about the fact that the number of participants of your computation cannot change at runtime. Right? While your application is running, if you're writing an MPI program, you can't add or remove nodes. This totally doesn't fly in this world, because you might be offered 100 machines for free. For sure you want to add them to your computation. And lastly, we have some low latency communication libraries that just are not fault tolerant, but instead are low latency in between two nodes for those cases where you have a graph computation where you send small messages along. We also have storage and checkpointing. We will not touch much of that during this tutorial. Okay, coming to an end of the first hour, I hope I instilled on you that resource management is upon us. There's really no way to write distributed applications for the predominant big data platforms, which would be Hadoop and its variants, without considering resource management underneath. Just as an additional point, if you think about the two biggest cloud operators right now, Amazon has spot pricing for their virtual machines. So the price goes up and down based on how much demand there is. Azure, on the other hand, bills by the minute and doesn't have spot pricing instead of hours. So at Amazon you pay for the hour, at Microsoft you pay for the minute. Now just imagine a world where these two good ideas cross, where you're sitting on computational resources that change price once a minute, or ideally more often, right? Because you want a more perfect market for this. Now you're sitting there computing gradients or passing messages or whatever on 100 machines, and the number of and the price just doubled. What do you do? Do you kind of shut down half of your machines, or do you hope that you converge fast enough, or what do you do? Those sorts of questions will come up on the public cloud as a utility. They don't right now because these two thought streams haven't crossed yet, but I'm pretty sure that it will happen. I believe, and I have to, right, because I invested 2 years of my life into it, is that Reef provides a useful abstraction in this world, where it's not too high to be useless for many applications, but very useful for only a few. It's also not too low in the sense that it doesn't help you anything. It doesn't help in principle. It does not take away any principal problem of writing a distributed program. It just makes every principal problem of writing a distributed program practically very accessible. So when a machine fails, we tell you. You don't have to figure that out. When a task is done, we tell you. You don't have to figure that out. When you have a resource allocation that's satisfied, we tell you. You don't have to figure that out. But what to do with that information, kind of the hard part of building distributed algorithms, nothing of that kind is in Reef at this point. And it shouldn't, because it should have broad appeal. So I had this title about resource-aware machine learning. And I'm going to just postulate that that looks like a promising idea. And I've told you nothing about it, but as always in talks, I'm just going to demonstrate it by graph. In this case, I conveniently left out not most of the information. But if you think about running on a cluster or a cloud, and you require 254 partitions of data to be loaded. So a very naive way, and you run gradient descent. This is a variant of gradient descent run on the gene expression data set that Langford et al. Used in the TerraScale learning paper. A very naive way would be to go to your resource manager, ask for 254 machines. When they are all there, you ask them all to load the data into main memory. When they're all done with that, you commence your or reduce operations. That is the red line. So you wait for a long while, in this case on a loaded cluster, 10 minutes. Then you wait a little more to load the data, and then you see the learning curve that you would expect. Now, okay, this cluster might be terrible, and you had to wait for 10 minutes even for the allocation. So what if you would subtract the whole allocation time from this and had an ideal cluster that is all to yourself? You just go there, you ask for 254, you get them immediately. That's the green line. The green line is a lot better, obviously, but it's still pretty bad because you still have to wait for the slowest of the machines to load the data before you can either enter the first iteration or exit it. At one of these 2 points, you have a barrier where all of the machines have to have checked in. And as I was saying when I referred to the one slow reducer, this can actually happen, right? You can have situations where machines are slow. Lastly, the blue line is something that we call ramp up. In this case, we say, well, there are all these lovely papers that say that you should do some learning on a subset of your data, and once some statistical condition of your model is met, add some more data and continue. So say, okay, what if we replace the statistical condition with the system and just run on, let's say, 4 machines, 1 iteration, and whatever machine became available in between takes part in the next iteration and so on. So in this case, the first iteration actually only runs on 2 or 3 actual partitions of the data that we had at the time rather immediately. And then, of course, as you would expect, in the beginning of your optimization, it doesn't matter that much that you have a lot of data. So we can do much, much faster. And I would call a graph where a quote-unquote promising approach is done before the current state-of-the-art can start very promising. Okay, there are a couple of developments by others on Reef that I wanted to highlight towards the end of today. One is Surf. That's done by Seoul National University and SK Telecom. They built an in-memory file system in Reef. Because memory is getting cheaper, the data sets are also getting bigger, but the important ones often don't. So keeping things in main memory is an interesting approach. Grouper is kind of a generalization of the MPI primitives and what you would call a shuffle phase in Hadoop. How can you make this more general? Because whether you do an MPI reduce or a map reduce job, it looks a lot alike from some angle. A quick statement on the status of the project. The code has been released on GitHub. It's Apache 2 license, so that should give no one who works for a company in the audience trouble using it, touching it, and all that. We do time-based releases. That means on the 21st of each month there is a release. The very fact that I'm here this week means that the release on the 21st of this month will be a little less in volume than others, because we don't say the following features are a release, we just make one on the 21st. We are currently on version 0.5. For the summer school, we will use version 0.6 snapshot. We tried it on all the various Hadoop distributions we could find. That's it for today, and I think I'm perfectly on time. Thanks. Yeah.
Why did you keep the decision to use Java as a language?
Why did we keep the decision to use Java as a language? It's easy to integrate into the both technical and social community around Hadoop.
They were just because it's Hadoop based.
Yes.
How does this compare with Spark?
How does this compare with Spark? This is the most asked question. So if you think about, if you had Reef, building Spark would be easy. The other way around, not. So Reef occupies an ever so slightly lower layer in the stack of big data tools. So if you think about how would you implement a parameter server in Spark, the answer will be some sort of line to the underlying system. If you would say how to build a parameter server in Reef, I would say come talk to me. I would love for someone to do it. Right? It's very straightforward to do.
Do you run anything else than Yarn?
Yes, we do. We have, and you will come in touch with that. If we are unlucky for all of the summer school, the local runtime, which just simulates containers on your local process. We have some networking issues to our cluster from here, which is a bit unfortunate. So we have a local runtime that's pretty awesome for debugging because you just run locally. You can just connect with the debugger to your containers and just talk to them. Then the guys in Korea are working on a port of Reef to Mesos, which is the other open source resource manager. There's nothing in principle that stops Reef to be ported to any resource manager. As a matter of fact, we have that as an abstraction layer in the software because that's one of the value props of Reef. To write it once, and if Yarn wins and you originally set on Mesos, then you're good, and the other way around. Yeah?
Are there any default policies that you do provide?
Yes, I'll go over them tomorrow. But in general, we try, whenever you don't listen to an event, we either shrink your computation. So if a task is done, we will return the evaluator if you don't do anything. Or if there's a failure, we declare job failure. We try to make your computation cheaper. That's the default policy. Okay. We're 2 minutes over to coffee or something. So let's end it.
I feel like there.
We have actually okay.
Yes. There's actually quite a bit of theory to it, why it works. Yeah. Yeah, I mean, for people who have not built distributed systems, it's but it's incredibly hard. Yeah. It is good. It's an independent that sounds good. Tag is mechanism helps you figure those things out. It's one of the policies that we only do this this object depends on, let's say, a file. It depends on the file. But he can't tell you whether it's the right that depends on the C# side. So we have implemented Reef in Java and C#. The C# side is very straightforward, but that requires you to have we have to try on the Java side. We haven't written what we are doing is to drive it. We have bridges into various languages so that you can write your intent. The evaluator, the runtime for the task, we re-implement programming. We have some interest to do that. We haven't gotten the time and volunteers to do it. Yeah. Yes. Yes.
Here's my business
Yes. And we haven't gotten around to building it yet. It should be fairly straightforward because Zeno is all network-based, and driver. So you need to fill out some protocol options and send it out and stuff. It's not